Okay, let's get the session started. Welcome everyone to this Thursday morning session in the Julia General section. And I'm delighted to say that we have a really exciting talk with a real live musical instrument to start us off. So we have Antonio and Dario here who are going to tell us about building playable virtual instruments in Julia, which sounds super cool. I'm very much looking forward to it. And I'll pass over to them to get started.
Okay, thank you very much. Good morning, everyone. My name is Antonio Ortega Bruch, and this is my colleague, Dario Ruiz. We are PhD candidates at the National University of Quilmes in Argentina. Today, we will show you a custom hardware interface for playing virtual instruments built from ordinary differential equations in Julia. We are interested in saxophone acoustics from a nonlinear dynamics perspective. In particular, we want to understand how a low-dimensional system of ordinary differential equations can reproduce some of the complex behaviors we observe in the instrument. But we don't want to solve the equations only to plot the results of line. We want a model to run in real time, so it can be heard and played as an instrument. And a playable virtual instrument is a demanding task. The system must run continuously, be responsive, and stable enough for a performer to interact with in real time. Julia gives us access to high performance ODE solvers, and we want to keep the model, the numerical integration, the dynamical analysis, and the real-time performance all in the same environment. At JuliaCon 2024, we presented a small package for some synthesis from ordinary differential equations named Real-Time Audio DFQ JL. We are seeing a small code example here. It uses differential equations, JL, and live-port audio to integrate a dynamical system in real time and send the solution to the audio output. So you can hear the system as it evolves and change its parameters live from the repo while it's playing. And now we are using that same package to control a mathematical model of the saxophone in real time using an instrumented mouthpiece equipped with sensors, with pressure and force sensors that you can see here. And we will show you a short demo at the end. Here's a diagram of the saxophone model. It's a minimal, low-dimensional model. The goal is to capture the essential dynamics, not to sound fully realistic. It has 3 parts, 1 degree of freedom oscillator for the reed, driven by the pressure difference across it, a nonlinear equation for the airflow through the reed channel, derived from Bernoulli's equation, and a model description of the impedance of the saxophone bore. The 2 control parameters are gamma, the normalized blowing pressure, and zeta, the effective channel aperture. And this is a diagram of our setup. This is the instrumented mouthpiece. You can see the pressure sensor here, which measures blowing pressure inside the mouth, and the force sensor here on the reed, measuring the force applied by the lip. These are read using an Arduino board and streamed to Julia over serial. And in Julia, a separate task reads that stream using libserial_port_JL. The blowing pressure is mapped to the control parameter gamma, and the force of the lip is mapped to the control parameter zeta of the model. And finally, real-time audio defect integrates the model, updates its parameters in real time, and sends the solutions through the audio interface. To test the model, we conducted an experiment with 14 experienced saxophone players. Each participant performed 5 tasks in 2 blocks, including ascending and descending octave jumps and a multiphonic in both the model and the real instrument. For example, here in the legato descending, the player goes from the high register to the low register without using any key, just controlling blowing pressure and the force of the lips, the two control parameters of the model. And here in the multiphonic, they are exciting both the high and low register at the same time. And now to show you some preliminary results, we have a bifurcation diagram in the parameter space gamma theta computed using bifurcation kit, where the different bifurcations are displayed with thin color lines, and superimposed is a thick trajectory showing the evolution of the parameters as the saxophonist plays the task. Here, for example, for the legato descending task, the player starts from the square after a hop bifurcation that gives origin to the high register in blue, and then moves crossing an A mark sucker and the period doubling bifurcation that destabilizes this register, and then falling to the low register in red. And here, for the multiphonic, the trajectory stays close to the destabilizing bifurcation, where both registers interact. So, by way of conclusion, we've seen that a low-dimensional dynamical model can become a playable instrument when physically meaningful parameters are controlled by a performer. And Julia allows us to use the same implementation for simulation, dynamical analysis, and real-time audio without translating the model into a separate sound synthesis environment. Making the model playable also helps us build confidence in it by testing whether a performer can reproduce relevant qualitative behaviors observed in the real instrument. And for the future, we are planning to incorporate the vocal tract in the model and also in the hardware interface, as we are aware that it might be responsible for some of the behaviors we see in the real instrument. And now we promised a live demo, so Dario will play some of the tasks we've seen earlier, changing register by controlling blowing pressure and force on the reed while maintaining the same fingering. We are seeing a real saxophone, but what we will hear is actually the model. Let me go to the REPL. Okay, I think that would be it. Do you want to hear more of the model? Okay. Maybe the multiphonic ones. Okay. It's a little bit difficult to get the multiphonic, but it's also in the real instrument too. So. Okay. Before leaving, we would like to thank to Christoph Heimbach, who kindly lent us his saxophone for the demonstration. Well, We have prepared a video backup in case it didn't work.
But it worked.
It worked. And thank you, all of you.
Okay, let's thank our speakers again. Yeah. Okay, that's great. So we have plenty of time for questions. So who's got a question? One up here.
The question is how well does the model handle the, I guess, most irritating portions of the instrument to play, right? Like G, G sharp, A, especially crossing the octave.
In this case, we are showing only one fingering, and we don't have a dynamic control for fingerings. And so now we would have to stop the model, let's say, and change it. But it's doable to control it in real time too.
Yes, we have not implemented now, but changing fingerings, it's just a matter of change parameters in the system. So,
yeah. Thanks. Another question over here.
Yeah, first of all, thanks. It's very cool. I think having played with MIDI saxophones, I always missed these, non-quantized notes and transitions that you can actually play on a real instrument. So this was actually very interesting to see. What I was wondering is, I imagine that if you model saxophone playing just with the pressure on the reed and the air pressure parameters, you're missing out on some things that you can do with a saxophone. Like you can, for example, stop the vibration of the reed with your tongue. Do you have plans to incorporate such things?
Yeah. Well, the vibration of the reed, it's maybe the most difficult part. The saxophone players we worked with reported that one of the missing features in feedback was the vibration of the reed in their lips. Yeah. So right now we are thinking in more in incorporating the vocal tract and the resonance of the vocal tract to the model. But that could be the next step.
Thank you. Yeah, great. We have another question all the way at the back, which keeps me fit. Don't apologize, it's fine.
Yeah, that's really cool, I think. And I was thinking, it does allow you to play silently, right? Because that didn't exist before so yeah. And I was thinking whether that's like a reed math piece, and I was thinking, is it possible with like a brass one? Have you planned anything in that direction? Because, yeah.
A press what, sorry?
A brass math piece like trumpet or something.
Yes, in fact, the same model can be adapted to a brass instrument by changing some parameter values. Yes, we could.
Yes, and according to the first question, it's all sound synthesized, so you could have it in your headphones.
Yeah, that's really cool to play like in the evening or at night, because I really missed that. Thank you very much. It was a very nice talk.
Thank you.
Okay, thank you.
Excellent. So let's thank our speakers again, and I think we'll move topic now.
Thank you.
Hopefully this will work. Fantastic. So, yeah, so our next speaker, we're going to change topic a wee bit. I think the title in the agenda was The Hidden Path to Turing.jl, but it's now 2 years with Turing.jl, but I'm sure it's going to be a good story. So I'll pass on to Penelope, who's our next speaker.
Hello, thanks for being here. So the talk title is a bit different, and the main reason is because I wanted to de-emphasize version 1 of Turing, which is not actually really happening, and to talk about my experience working on Turing version 0. I only have 15 minutes, and as I learned the other day, that's quite a large compression factor. So I'm going to have to give a really, really quick whistle-stop tour of everything. So I'll start with an overview of what Turing is, and then I'll talk about 3 nice things that we did during these 2 years. I'll talk about a couple of things to improve, so the content is still going to be kind of similar to the abstract, but really pared down. And then hopefully at the end we'll have time for questions, and maybe there'll be more than one question. So what is Turing? So Turing is one of the more popular, more highly starred repositories in the Julia ecosystem. It's for probabilistic programming. The stars didn't help me get Claude Max 6 months though, by the way. So it has a macro that lets you express probabilistic functions in Julia syntax. So for example, here, the mu is not a number, but it's actually drawn from a distribution, a normal distribution. And you can mix and match normal Julia syntax with your models, so like the for loop above, that just works as expected. Once you've defined your model, you can put in some data, you can pass in some data, y and sigma in this case, and then perform inference on it. And in this last line, we're using MCMC sampling and the nuts algorithm. So I worked on Turing.jl for 2 years, roughly 2 years, starting from 2024 until a couple of months ago. And you might have seen me on the Turing channel in Julia Slack. I attempt and sometimes fail to answer people's questions. But really, it's because I'm a software engineer, right? My background is not in Bayesian statistics. I did chemistry, and then I moved into software engineering, so I'm not a statistician at all. And that's something that we'll come back to. But even a software engineer can come up with like things that they think are good for software, right? One of them is modularity. And to kind of explain what I mean by that, it's easier to give an example. So this is the state type that Turing used to use at the start of when I started working on the project. And it has this like single struct that's called variable. It's got a dictionary that stores your values. So for example, it maps mu to the value 1.5 or whatever. It's also got a field that calculates the log probability density associated with all the random variables. And that's just a real, and then there are other things as well. Now, the problem with this struct is that you can't extend it. So let's say you've got a complicated inference algorithm that needs more information. You can't just bolt on a new field into your struct. And you also can't trim it down. So if you don't need your values, if you only need the log probability, you can't get rid of that dictionary. It's there whether you like it or not. Another more worrying thing was that this values dictionary sometimes is being used as both input and output. So you'd run your model with one of these variable things, and then it would say, well, I'm going to use the value of mu from inside that dictionary, and then write it back into the dictionary. I was like, what? So one of the big things that we've done in a series of refactors is to change the structure of this variable thing. And now it's a tuple of what we call accumulators. And you can have different accumulators that accumulate different things. So for example, you could have one for values, you could have one for your log densities, but in fact, we have 3 different log densities. We've got the log likelihood, the log prior, and then the determinant of the Jacobian if you've got transform variables. And that allows you to keep all of these things separate and to report these things separately. Apart from the outputs, which are stored in accumulators, we also have initialization strategies. These are the inputs. And if you declare like custom subtypes of both of these things, you can have very, very flexible, very customizable model evaluation, which is a really nice thing. It's a little bit verbose, but it's very, very powerful and much more decoupled compared to what it used to be. And then as software engineers, we also care about performance. over the course of the last 2 years, we've had a lot of PRs and improvements over this period that have led to much greater performance. And in particular, I'm talking about overheads. So if you've got a big distribution and big data, and then you call log PDF on your distribution data, we can't make that faster, right? But all the other stuff that goes on top of that, like Turing's injection, like the stuff that Turing injects into your model, that stuff is really, really trimmed down. And a lot of that just comes from like judicious use of accumulators. So don't accumulate values when you don't need to, just don't need to do log P when you need to. But also there are bits about new data structures, and varname tuple is one of these things which I'll touch on the next slide. It turns out that if you take reverse mode enzyme and you use it as your AD backend with Turing, you can get performance that's faster than Stan in many cases. Reverse mode enzyme is the fastest AD backend that we have. Fun fact, Turing actually requires you to use runtime activity of enzyme. So if someone finds a way to get rid of that requirement, it could be even faster. Okay, and then the third thing that I'm going to talk about is something called fidelity. And this comes back to this type called varname tuple. Varname tuple is a generic type that maps variable names to values. So it's kind of like the dictionary before that, but it's got extra special stuff built in, such that it recognizes the structure of your model as you wrote it. So for example, if you've got a vector x in your model, and then you sample each element of x individually, so x1, x2, x3, tilde something, varname tuple will recognize that all your xi's came from the same vector x, and then it'll put them back into a vector for you. And because this information this is a data type that's information rich, so we can use this fearlessly everywhere inside Turing, regardless of whether you sample from the prior or whether you get a point estimate by running optimization on a model. These processes now all give you the same data type, which is a varname tuple. Previously, they would give you all sorts of random junk, and then you'd have to like convert between them. You can then use this set of parameters and feed it into MCMC sampling. You can use it as like the initial starting point for your MCMC. And when you've done MCMC, we've also got a new data type called a flexi-chain, and this is a chain type that preserves the shapes as well as the types of your random variables. So for example, if you've got a Poisson variable that's supposed to be an integer, if you used MCMC chains or JL, this would just get converted to float, and then you'd have all sorts of issues if you tried to run this into a model again. Flexi-chains would preserve that as an integer, and then it'll preserve vectors as vectors, for example. And it comes full circle, because if you were to take a flexi-chain and call rand on that, you get back a varname tuple. So the entire ecosystem in Turing is much more consistent, and in my opinion, a pleasure to use than before. I should say that flexi-chains is a package that I'm still maintaining in my kind of spare time. I'm not working on Turing anymore, but I'm still working on this. And it's not just meant for Turing. So if you've got any package that generates MCMC outputs or analyzes MCMC outputs, get in touch, and I'd love to put an extension in if we don't already have one. Okay, so a couple of things to improve before we get to questions. The first thing that I think that we could have done better is about identifying the users of Turing. So Turing's got like 2,000 stars, blah, blah, blah. I put that in my CV, it's great. I don't actually know very well who's using Turing out there in the wild, right? I don't actually know who's trying to use this to do research, to push the boundaries of knowledge. And like, as I said, I'm a software engineer, so this is my favorite model. Like, it's got a price, it's got a likelihood, it's got everything I wanted. But no one's doing this in production. So we really needed to reach out to more users, because we did reach out to some, but we needed to understand what pain points exist, what walls people are running into when they use Turing. I tried to do a little bit of this by publishing newsletters. So I used to run a regular newsletter on Julia Slack, on the Turing website, and on GitHub. And this is really nice because it lets us get to Julia people, Julia users who are maybe using Turing. But also, there's a problem there because there's a whole world of people outside of this. There are people using Stan, using NumPyro, using all sorts of PPLs that are not Turing, and all sorts of languages that are not Julia. And we really think that, well, I really think that we should have kind of reached out to some of these people better to kind of advertise Julia, to advertise Turing, to say, well, look, even if you're not going to use this thing, it's pretty cool and it exists. So that's the other thing. Overall, I just think that we should challenge ourselves to do better, really, because it's very easy to say, well, okay, we've made this a good library, we're really happy now. But, where is the growth coming from? Where is the new direction going to? And with that, I think it's almost time for questions. I just want to say a quick thank you to everyone I've worked with on Turing, but also everyone who's engaged with us on GitHub, Slack, or in real life. That's really been the best part of working on this. And you for listening. Now, because this is quite a short talk, I do have a longer version of it, so you can read that if you want.
Okay, fantastic. I see hands going up already, so I'll run up the stairs to take some questions. I think I saw yours first. All right.
Thanks, that was a really amazing talk and really great work. I was wondering, if you were going to develop a PPL from scratch and you had like a few years and a small team, would you do it in Julia, and what other things would you be thinking about?
So I think Julia was a big advantage for Turing because it was a small team. I think you know exactly what you said. And it means that we don't have to reinvent the wheel when it comes to distributions, differential equations, GPs, blah, blah, blah. We don't need to do any of that ourselves. Whereas if you compare it to something like Stan, they have to write everything themselves, right? And autodiff as well. Yeah, so basically, I think I would say that, yes, Julia, but what was the second part of the question again? Sorry.
Sorry. Is there anything else you'd think about beyond just language choice?
Oh, no, I think it's tricky because I think I would still stick with a lot of the same things that Turing did. I would stick with a macro-based syntax, but also I think I would be a bit more keen to introduce new syntaxes. So Turing right now has very slim syntax. It's basically got a tilde, and then that's basically the only special syntax in Turing. I mean, there are a couple of macros, but you know, that's all. So I think that if you wanted to have something that was richer, something that was more amenable towards like custom inference algorithms, it might be necessary to insert more primitives in that sense. But largely, I would say that I would stick to a lot of what Turing did.
Thanks.
Hi, thank you. My question is, so whenever I look at my code for like my custom models, and I think this just looks ugly, and I wish I would just can use Turing and write this down in a nice, concise way. The thing then where this fails is then when I have integer latent variables. So it's like somewhere in my models I have like, I just have to like choose a category or something. And then this like always fails in some funny way with AD or something. Is there like a go-to recipe how to deal with this kind of situation?
So with AD, like you're not supposed to differentiate integers, they're not differentiable. So you can't use something like HMC or nuts, it will error if you do that. There are other inference algorithms available that are not so interesting. So you could do a dip sampler where you use a different sampler for the discrete variable, and then you could use HMC for the rest. But probably, you know, like if there are any Stan fans here, you know, they would probably argue, and Suffix, a wonderful person, he would also argue that you should marginalize out the discrete variable. But we don't have an automatic way to do that in Turing, so you've got to kind of manually do that yourself.
Excellent, thanks very much. Let's thank Penelope again. And the next speaker is Alexander, I believe. Ah, here you are, okay. I'll let you get set up. Do you want HDMI or USB-C? You can. have Alexander with us, who's going to talk about neural networks, genetic algorithms, and neuroevolution. This is practical artificial intelligence in Julia. So I'll let you take it away, Alexander.
Hi, I am Alexandre Bergel. I'm French. I've been living in Germany for exactly 2 weeks today. So writing a book is really a lot of fun. It doesn't make sense, from an economical point of view, like losing money all the time. But at least this is really a lot of fun that I would like to share with you. So the book is divided into 3 parts. The first one is about neural network. Neural network. This is a metaphor like to make, something that looks like how the brain works in a computer. And genetic algorithm, the second part, is about a metaphor like to make how to model how biological species evolve over the time. And then the third part of the book is, we take the result of part 1, result of part 2, we combine, and then we have something that we call neuroevolution. So the idea of this talk is really to give a glimpse, just a rough idea, like, but what the book is about. So we'll do a lot of demo. I think everything will work for it. So the first part, neural networks. Before talking about network, let's talk about a neuron. And we'll take the very simple definition that was proposed in 1953 in a seminal paper that described how to express neuron on a computer. Interesting to see that, as soon as the human had a computer, they tried to simulate brains and evolution. Very interesting. So a perceptron, this is a small machine here that is able to make a decision. In that case here, I have 3 inputs, x1, x2, x3, and not all of the input have the same relevance. You may have some input that are more important than the others. I mean, if you think about image recognition, like on a picture where the faces are, I mean, probably the pixels at the border of the picture will not make much, will not be that important. So we express the weight, the importance with the weight. So each input has a weight. And then a perception works that way that when we sum the weighted input, then if the sum is below a threshold t, then the perceptron fire 1, else it just fire 0. Okay, so what can we do with this perceptron? So imagine that, you love metal music. This weekend there is a great concert, and you would like to go to this concert. And there is maybe a number of factors that you would like to consider for you to go to this concert. Like, will the weather be good? Maybe you don't want to bang your hand in the mud, or maybe you want. And, like, maybe you don't want to go there alone. If someone accompanies you, then this is an important factor. Or if you are like me, you don't like to drive, it could be important that the concert happens near a train station. There could be other factors, such as the price of the concert, whether there's some previous band. And then you can build different models based on some value for the weight and the bias, the threshold. For example, here the first one, in that case, it's very important that someone accompany you. So it means that if I have for the first factor and the first input and the third input, I have a value of 2, and then for the second input, will someone accompany me? It's very important. So he has a high weight, and it means that. Given that model here, if you want to go to this concert, then you need at least to have the first input and the first and the third input to be 1, to matches. Else, just the second one, is enough for you to go there. Or you could have a different factor that you absolutely want to go there, without a car. So it means that the third factor will be very important. So just a word about the threshold, the bias. So it's very if you have tendency to reduce the bias, then it will be easier for you to go to the concert. If I have, for example, a threshold of 1, then any of these 3 factors here will be enough for you to go there. If I have 5, then at least I need, I need a second factor here to comply. Another simple application you can do with this perceptron is to express logical gate. So here I have another perceptron where I have 2 inputs, x1 and x2, and each of these has a weight of 1. And then here the threshold is 1.5. And then using that perceptron, you can express the AND logical gate. So, if I have 0 and 0, for input, then I have 0 times 1 plus 0 times 1, give me 0, which is lower than 1.5. So the perceptron will fire 0. On the other hand, if I have 1 as if I have 1 for both inputs, then the sum will be 2. 2 is greater than 1.5, so I will have the result of 1. And yeah, and now what I like to do is with my students is undergrad students say, okay, let's take a piece of paper and find the weight and the bias, the threshold for to express the OR logical gate. I mean, it's not complex. There are 3 parameters. It will take a few seconds, maybe 1 minute, for you to find it. And this is one answer to this. But if as soon as the number of parameters scales up, even slightly, you can't do it by hand. So you need to have a smarter way to actually find out, like, what would be the bias, those parameters, in order for my perceptron to express some behavior that I would like it to be. And so finding those parameters actually involve an algorithm, and this is where you have this simple algorithm here can make you a perceptron learn. So this is a very basic gradient descent algorithm. So for a given example, this is a set of input and 1 output, then you can, first you compute the difference. Your perceptron maybe can already do the behavior you want it to have. If not, then you compute the difference, and then if you have diff equals 0, then your perceptron does what you want it to do. Else you need to update the weight and the bias. So here you have this learning rate, a very small value, close to 0. And then for each weight, you take the previous weight, and then you add the result of multiplying the learning rate by the input and the differences. And you do the same thing for the bias. And when you do that for each example, and once you do that a number of times, then your perceptron can do the thing you want it to do. So here a small example. So here I create a perceptron with some random value parameters. So this is a NOT perceptron, and we'll teach it how to actually express the NOT logical gate. So we are training here the perceptron that if it has 0 as input, I wanted it to return 1. If it has 1, it returns 0. Then if I run that thing here, I see that NOT 0 is 0.59, and NOT 1 is 0.7. So we are kind of away from the result we expect, so it means that we need to train a bit more, and even I think even 1,000 should be enough. Yeah, so NOT 0, which is 1, we are getting now closer to it. Before we were here, now we are getting here. And it means that more training you provide and closer to the result you want it to be, you are getting to. And here this is another example. So this is really an example that there is in the first part of the book. So I show you an example that comes from the first chapter and the second chapter. So the first chapter is about the original perceptron model from the 1953. Then we have the sigmoid neuron, where we bring the activation function. And then once we have a perceptron, a neuron, then you can start to combine them in order to have some neural network. And then chapter 4, there is a bit of theory about learning, like why the gradient descent work, and what is really the essence of it. And then chapter 5, which concludes the first part of the book, is about like some simple data classification problems. Like you have the iris, flower, the seeds, very simple examples in machine learning. So the first part of the book is about neural network. I think this first part gives, gentle introduction of what are neural networks. It doesn't go deep at all, but it gives enough material to be used in the third part when we talk about neural evolution. So now here comes the second part of the book about genetic algorithm. So it has been formulated as one of the base of evolution of biological species is to have, the individuals that are strong, then they are likely to live longer. While the individuals that are weak will die soon. I mean, in a place where with rabbits and wolves, you know, the rabbit that can run fast, they have better chance to escape the wolf. And if they escape successfully, then they will have better chance to reproduce themselves. And then their offspring are likely also to run fast. While the rabbit that cannot run that fast, then they will be eaten very quickly. Okay, what does he mean here on a computer? So here we have a friend that would like to play a game. He say, I will guess a 3-letter word in my head, and you need to search for it. You need to find it. And so what I say here, word, is actually like a sequence of 3 characters. It doesn't mean this is a real word. This is just a sequence of 3 characters. And then the secret word is cat, C-A-T. And as a hint to find the solution, that superhero here will tell us the number of letters that matches the secret word. For each attempt, each word we'll give, it will tell us the number of letters that matches here. So we can try. We have C-O-W, cow, and this word here, cow, has a score of 1, because the C here matches here. So there is 1 correct letter. You can try randomly, to give another word, pause. Then this one has a score of 0. Or you can also have gas. And this one has a score of 1, because here there is the A that matches here. So we did 3 attempts. We didn't find a solution. Some of the attempts were bad, because the score is 0. Some attempts were a bit better, because we got a score of 1. And, okay, so this is the first generation of words. So we have 3 words, and some of them are good, some of them are bad. A bit better, and some of them are really bad. And then, if you remember, from your biological classes at the college, the way that the genes works, the chromosome get transmitted to the offspring from the parent. You have some operation. You have the crossover. We take one part of the gene of the father and one part of the gene of the mother, and then you combine them, and then you have a new chromosome. And we are doing here the same way with our chromosome, digital chromosome. For example, here we have, at the first generation, we have gas and cow, and maybe, these 2 words will be picked up, and then there is, this word will be cut here, where we take this first letter and the last 2 letters here. This will produce a new word, go. This one is not very interesting because it has a score of 0. So this word didn't get us closer to the solution here. But we could have, the C here that get appended AZ here. And this product CAS. And then we are getting a bit closer to the solution because there's a C and the A that matches here. And we could have another append. So in that second generation here, we were closer because we got CAZ. And then we can, the second genetic operator that, if you remember your biology classes in the college, then there is also the mutation. Randomly, we can, change one gene for another, or one value of a gene for something else. For example, here the W can be changed to a Z, or the Z can be changed to a T, for example, or O to A. So in that case, here we found the secret word, and using some basic principle of biology. And here we found the solution using 3 generations. We had we had 3 initial words, and we make them evolve until we reach the solution here. And this is what we are doing here. So here we have this distance function that tells us the number of letters that matches the secret word, and the secret word is CAT. And here we run the genetic algorithm. So we have a gene, which just be a value between A and Z. And here I want how long the chromosome should be. Well, this is the number of letters that there is in the secret word. And I want the population to be 100 words. So I will have 100 initial random words, and then I will make this evolve here. And then I end up when the fitness, the score of a population is the length of the secret word. It means that I found the solution here. Then I run here the algorithm, and then I see that I found the solution here, because I run until generation 3. There are 3 generations here, and the score of the first and the second generation is 2, and while the score of the third generation is 3, meaning that the algorithm ends, and we found the solution here. And we can have a different secret word. Hello, Julia. And then here I run. Then it took 15 iterations to find the solution here. And obviously, if I increase, if I decrease the population size, instead of having 100 words, I have just 10, then it would take much longer to find the solution. And if I increase the population size here, let's say of 10,000, then just 7 generations I need to find the solution here. Okay, and that's really the way that genetic algorithm works. And so in that example here, if we provide as a value of a gene a letter, and then we provide as a fitness function the distance to the word cat, then the algorithm will find the word cat. And if I provide, a list of cities, and then the fitness function will be the length of the path to traverse all these cities, then I will have as a result a solution to the traveling salesman problems, which is the shortest distance between the different cities, to visit all the cities. And then something fun is, if I provide some numerical values that will be interpreted by the fitness function as a property of a muscle, such as the length, the force, the times it takes to cycle between being small or big, then, and then if you also use a small physical engine and make those creatures walk, then you can have actually creatures that can walk. So here I have some random creatures that do nothing, they just behave, they are completely random. So we see that each circle here is a join between different muscles, and this gray line here are muscles between those joints. So this is like a small creature, there is no bone, it just moves. Currently, we haven't trained that creature to actually do something interesting. So, now we not do the training because it takes like a few minutes to actually train that, but here this is the result of a training. So here, I think I use like 500 generation, and here there is the result, 3 creatures taken from 3 different generations. The green creature here, that is able to move to the right, is the really result of the algorithm, and the yellow is in middle of the evolution, and the red creature is close to the first, to the beginning of the evolution. So yeah, so the green creature went through a long evolution, so it's much smarter at doing something such as moving to the right. He can climb stairs, he can even jump. There are many things he can do. We can really make it evolve to do some interesting things here. Okay, so the second part of the book is divided as follows. So the chapter 6, we just show what are genetic algorithms, and with some very simple examples. Then chapter 7, there is a number of examples and competing examples that solve some classical, that give an answer to classical algorithmic problems. The chapter 8 is about the traveling salesman problem. So this is really interesting because you just want to go through each city just once. So there is, you need a different genetic operator here. And the chapter 9 is really about building creatures. So they present a small physics engine and just to make creature live. And then the chapter 10 is about evolving those creatures here. So this concludes the second part of the book. And the third part of the book takes the result of part 1 and part 2. So in part 2, like in the small example, I make those creatures evolve that were just a set of numbers here. In the third part of the book, we actually make neural network evolve. So deep learning, is very greedy in examples. So in order to have deep learning works in a nice way, then you need to have like good data. For example, if you want the neural network to distinguish a cat from a dog, roughly you need 2,000 pictures. 1,000 pictures for a cat, 1,000 pictures for a dog. It's not really the way that humans learn. And that was really the main motivation of neural evolution. How can we have a model that actually make it closer to the way that the species have evolved. So evolution of neural networks is called neuroevolution. So this is a fairly large research area. And the idea is to use the genetic algorithm not only to look for the weights and the biases, as gradient descent do, but also to find the connection between those neurons. So at the very beginning, the model, they have very few amount of neurons, and when we are evolving those neural networks, there are more neurons that get added. While in deep learning, you start with your millions of neurons from the start. But here we are doing the other way around. We truly have very small neural network, and we add neurons to it. Okay, and what can we do with that? One compelling example is to have those neural networks play video games. So here, this is a small example here where I have my superhero here that can jump. And the idea is, so there is I lost. But yeah. And what we do also in the book, not only to provide the code of that game, but also like to use genetic algorithm to build those neural networks and make them grow over the evolution here. So here, this is the result of an evolution here. The ants, yeah, so he won. I think we can even like make it a bit more challenging. I think that 18 monsters, so there are more monsters now here. And let's see. Yeah, it's complete. Okay, so the first part of the book gives this idea of neuroevolution. It gives a superficial introduction of it. Chapter 12 gives a full implementation of the NEAT algorithm. The NEAT was proposed in 2002, I think. And this is really like, so this is a very beautiful algorithm. And at least to me. And then chapter 13, we give the full implementation of that small video game. So it's very basic, but it's fun. And chapter 14 actually create neural networks and make those networks evolve in order to be able to complete the game. All the source code is available for free. I think you can just go to my GitHub project, and you have all the source code to play the game and for everything. So what the book is not about, it's not about like complex deep learning models, not at all. It's very shallow on it. We don't talk about transformers, we don't talk about language models or image recognition. But the book is give sufficient information about neural networks and also make you expert in genetic algorithm. There we go really deep. And also introduce you to the fascinating world of neuroevolution. And also give a number of non-trivial and, I think, compelling examples. And something I think that's very important is that it does not require any strong mathematical background. So even if, you can just program and enjoy it. So the future plan is maybe like having more examples about walking creatures. So currently there is no skeleton, but I plan to have some skeleton, to add skeleton at some point. Also maybe use an external physical engine for walking creature. I know that there is one in Julia, but I just haven't got my hand on it yet. And also go deeper into neuroevolution. So neuroevolution, the algorithm that I provide was found in 2002, and they are much more sophisticated. They also can do some image recognition or some very complex tasks that actually compete with classical deep learning. And also like reinforcement learning, this is a topic that I found absolutely fascinating as well. And I think he will probably get his book on one day soon. Okay, thank you. Thank you very much.
Thanks, Alexander, and showing us all those nice examples as well. So we're open for questions. One here.
Hello, can you give some good examples of crossover mechanisms for traveling salesperson problems?
Yeah, the thing is, when you have a mutation in the way that I just pronounced it, for the later, you know, the word that you want to find at the very beginning, when you generate some words, you may have letters that appear more than once. And the thing is, if you take two words that has one unique letter, but if you cross over those words, you might have some letter that gets repeated. So it means that the classical way of cross-cutting, the crossover and the mutation are provided, like they do not really work for the traveling salesman problem. Because for that problem, then the genetic algorithm will not really look for the solution, but instead look for a valid path, because you don't want cities to appear more than once. So that's why you need a smarter genetic operation for that. And there is one that I said, a non-ordered crossover, and yeah, everything is written in the book. But yes, so there are dedicated operation for that. And even like for the living creatures, there is, and for the video game, actually there are dedicated operators, genetic operators, because you don't want to cut, a neuron in two when you do the crossover. You want to cut it at the boundary of a neuron in order for it to work properly.
Thanks. More questions? Maybe I'll ask one. So it looked like all of your code examples are like scripting examples. Did you also think about taking advantage of like Pluto notebooks to do these things? Then you could have like nice sliders for the parameters.
It would have been nice. The thing is, no, I haven't used Pluto, but actually it would be fantastic to do so. Actually, I wrote this book because I wanted to learn Julia. So
Okay.
And now I know Julia, and yeah, maybe there are new things that can be done on that. So.
Okay, very good. Question from Tyrone.
Could you put your GitHub back on the screen so I can make a picture?
So I think it is, yeah.
And you're, yeah. Thank you.
Thanks to you.
Actually, that's a general point, I think, for everyone that's doing presentations. Pre-talks allows you to upload your talk as well, and that can be a really useful reference for people that may have missed your talk, or people who want to go and look back for things like references and links. It's a very good idea. Okay. Any last question? Oh, we have one over here. I'm going to take a shortcut.
Yes, thanks very much. I was wondering, because you show the creator walking, and at the beginning it looks like they are doing nothing. And I wonder, is there some case where it's actually nothing happens, and how long do you have to believe something will eventually happen? When do you decide to just give up on a specific scenario?
Yeah, like often at the very early generations, you will have something will happen. For example, in the case of the video game, of the Mario video game, then randomly at the very first generation, you find out that if you go right is a good way to do so. Okay, it would just randomly, you will have neural networks that will just, push the right button to the joystick. And this is an example to show you that really at the very early generation, you will have some improvement. And then you have tendencies then to reach a plateau at some point. So it means that if you apply those techniques and you see nothing in the first generations, it means that something is wrong. And one classical example is that the genetic algorithm is trying to build some reasonable candidate solution without really pushing the. For example, like in the case of the cities, then it will just find that the best way to minimize the path is to stay in the same city, you know? But you don't want that. You want to enforce to really move around different cities, so yeah.
Okay, thanks very much. Let's thank Alexander again and all the speakers in the session. Okay. So we now have a short coffee break. I know that, fortunately, as human beings, we have reached the pinnacle of evolution, and we can all walk quite fast, get a coffee, and then walk right back, because we restart in 15 minutes, which is not an awfully long time. So I hope to see many of you back for the second part of the session. Okay, great. We're live. Okay, great. Welcome everyone back to this session. So we have 5 talks lined up, and we're going to start with Oscar, who's going to tell us about some advances that he's been working on in the special functions package to add differentiability to some of our important special functions. So take it away, Oscar.
Thank you very much. So this is the story that started maybe 10, 11 months ago. And there were a few issues piling up about some missing derivatives. In particular, the beta densities were not fully working with Turing models, which was a bit weird. The student distributions, they were not fitable if you know that the multivariate student distribution in embeddedist has no density in distributions.jl. A first reason is that the density is a bit hard to implement itself, but a second reason is that it's full of complex special functions. I came onto this problem because the student copula gradients were missing, and I was trying to fit it, and it was not possible using the standard tools from the ecosystem. And so I started thinking about it, and then I realized that in other languages, these things can be done, and so there was something to do. And in fact, the common dependency, the common issue behind all these problems is this function. This function is the incomplete beta function, and it's the CDF of the beta density. It's also used in the CDF of the student and multivariate student models. And in particular, if you take its inverse in X, you get the beta quantiles and the probability transform and copula construction of the student model. In Julia, this function is implemented under special functions that beta inc, and its inverse is under beta inc inv. The problem of this function is that it's an integral, right? So to evaluate it, you need to do fancy stuff. It's not as easy as you could think. And that was the issue that we had. So if you simply load distribution and forward diff, you try to get the quantile of some beta function and get the derivative of these quantiles, and this says, and at the end of the stack, it says that beta inc if from special functions.jl does not have a method for dual numbers. Okay, so let's try to get one in. The principal function works for float 64. So why not just remove the float 64 condition to have it run on everything? But this was not a very good idea. In fact, the primary implementation is designed for floating point value. It contains continued fraction expansions that are valid up to a certain precision, and differentiating through them might not be, and in fact was not and is not in that case the best way to do it. The lesson that I learned this day is that generic Julia code is not automatically AD friendly, in the sense that here we had code that was doing fancy stuff to compute some float 64 value, and differentiating through it was not going to give me the gradient I needed. Okay. So yeah, this was the 2 options in front of us. So the first one, which was probably the wrong one, was to differentiate the primal program. So for that, you need to follow every branch to differentiate every recurrence and basically put dual numbers through the computations. And you will inherit the noise that you have at boundaries. You will inherit the noise that you have because the computation is an approximation. And you will retain a computational graph that is very large. So on top of the results not being very good, it's going to take a lot of time. And the second option, the smart option, the hard option, is to re-implement a stable formula for the derivative itself. It's completely opposite and orthogonal to what we are normally doing with dual numbers, in the sense that here we are saying that no, we will not use dual stuff, and we will try to re-implement the derivative itself. But it has the benefit of being much more performant, in the sense that you compute the derivative exactly as you want it. And you can test the gradient separately. You can reuse the symmetry and the tail swaps that were in the primal too, but you can choose what branch you keep or what branch you do not. And so the lesson here is that differentiating an approximation is not the same problem as approximating the derivative, of course. So let's go with my bare hands from the standard calculus. We can get the derivative with respect to x of this function quite easily because x is on the top here. It doesn't happen anywhere else. And so the derivative with respect to x is very easy to compute by hand. The shape derivatives are a bit harder because the function is much more involved into a and b. And there is a paper from 1998, Boyk and Robertson Cox, that basically gives you a recurrent continued fraction formula for the derivative with respect to those two parameters. And it outputs a thing that computes the primal and the derivative at once, which is exactly what you need. So yeah, this is for the beta inc, but we also need the beta inc eve, which is the inverse function. But for that, standard trick can get the derivative of the inverse from the derivative of the standard version by saying that the derivative of the inverse is the inverse of the derivative, which is a bit hand-wavy, but it's the way it works. And with that, we end up with the fact that if we have a stable gradient kernel, we can support both beta inc and beta inc eve at once. And this is, in fact, exactly what the chain rules core standard in Julia expect. And this is what we ended up doing. So, in fact, the hooking into the Julia forward diff and chain rules thing was not very hard. It's a few lines of code, but everything is hidden into this function here. That is the core of the computation. But the interface to have the rest of the ecosystem, distribution.jl, Turing, and everything using the code is actually pretty easy to do. Yeah. So to implement it, the first time, 10 months ago, I was not able to do it myself, but I've started by reading I started by reading the paper, and the paper had a joint S+ and a joint MATLAB implementation, and so I asked my favorite LLM to translate them to Julia. Took 2 hours, worked correctly, the tests were passing. It produces a bit of code that I cannot understand myself, but that wasn't the point. And then I started to ask people to take a look at it, and we finally end up with the result that this code was not licensed correctly, in the sense that it was a derivative work of something that was not copyleft, and so we could not use it in special functions.jl. So that was a pain, and we discarded it. But hopefully, Arno Wirkners, excuse me if I don't pronounce your name correctly, has had a Julia version that he did by himself, which he agreed to license under MIT, and from which I could relaunch the LLM pipeline to convert it to what special functions.jl required. So the lesson here is that everything that is published might not be usable in open source programs, of course, which I did not expect before, but that was the way it was. So I'm going to skip this one. So this is basically the checks, because we had an implementation, but we did not to validate it. We were not able to understand the code properly, so we did make a very thorough test setup for it. And this is basically the way that DevMotion and me are working since 10 months. We are trying to make sure that the implementation does what it should do. So this work will unlock a few things. The fact that we now have chain rules for beta inc and beta inc inverse gives us beta quantiles, gives us student PDF in multivariate settings, gives us the copula transform that go with it. It solves a few discourse threads, a few issues on several packages with only one contribution, which is a very good outcome for the work. And the thing is that, the amazing thing is that by solving in one package extension of special functions.jl with respect to chain rules this derivative, the whole ecosystem benefits from it magically, which is very good. So the three takeaways that I have is that the AD system that we have is beautiful, but it's just as complete as the numerical primitives that we can put into it. And the generic programming and the chain rules stuff helps, but when we have special function, we still need to implement some expert rules and expert derivative behind them. Otherwise, the system doesn't work correctly. The second one is that differentiating the mathematics is always smarter than differentiating the program. It gives you better code, it gives you better output. And the third one is that the pair discussion itself is part of the contribution, in the sense that in that discussion we commented, we highlighted issues, and basically reading the code itself doesn't give you the full picture, but reading the PR discussion, which is pages long, gives you a much more thorough picture of what is happening. So this is the pull request 506 on special functions.jl. And I also wrote a blog post on it if you want more details. That's it. Am I good in time?
Yeah, you're on time.
Okay.
I meant 5 minutes to go before questions. So we're open for questions. Anything that someone would like to ask? Maybe I'll start. You said that you used an LLM initially to do the porting of the code. And I have to say that this is, and then you hit this licensing issue. And I have to say that this is one thing that worries me a little bit as well, is that these LLMs are trained, this is more of a comment actually, these LLMs are trained on everything that they can find on the internet. And if you had just asked it to implement these derivatives in Julia, it may well have used a piece of license code to inspire its own implementation. And then who takes responsibility for that? I think this is something that with this like vibe coding landscape, people are maybe not thinking about sufficiently.
Clearly. And it's also a pain because since I did not implement it myself, we are working with a piece of code that we have a lot of trouble understanding. And validating it correctly is a pain in the ass, basically.
Yeah.
But the licensing issue is very, very problematic. And the fact that there was already an implementation and that the guy responded to us and accepted to put it into MIT basically solved it. Otherwise, we will have to go back to Boyk and Robinson, which are both retired now, and ask them if we can use this 25-year-old code under a better license than the one they had at the time. The probability of a positive outcome was very low.
Well, okay, great. Another question?
I'll extend from the previous question. If you, right, I mean, you implemented it with an LLM, you don't understand the code, and you also don't know where the LLM picked up that information from, right? Why even care about the license at all at that point?
No,
right?
because
like you have no idea whose code, whose knowledge, right? The license only matters if you write it yourself.
Okay. At the beginning, I especially gave the LLM the implementation, the S+ and MATLAB implementation, and asked him to translate this thing, right? And so the task was a translating task, but of course the LLM can produce anything, so you don't know. And it has been trained with things that are not open source, so everything that it produced should not be licensed correctly. That's the way it is, yeah.
So thanks very much for the talk. I have an unrelated question. How did you decide where should the implementation live? Because it could be in the extension of special function of chain rule score. Maybe another AD package would not use chain rule score, things like that. How did you decide where to put it?
Basically, there was the other function in special functions.jl already had a chain rule extension with the derivative in them, and this one was missing, so we thought that this was the right place to put it. Yeah. But otherwise, it could have been the other way around. The extension could have been into chain rules, but it makes more sense to have it live, in particular the chain rules one, it makes more sense to have them live with the primal, in the primal package. I think so.
Okay, great. We'll have to move on, so let's thank Oscar again for his nice talk.
Thank you.
Any discussion?
Oh.
One of my colleagues from the Hamburg light source community, who's James, who works just a little bit along the road from where I am in Daisy at XFEL, and he's going to tell us about the real-time analysis of XFEL data with a bit of Julia sprinkled in there, I'm sure.
For coming to the talk. Yeah, my name is James and I work at the European XFEL. So I'll be talking about how we do analysis of the data that we collect there. I want to start off by talking about what an XFEL actually is, because it's kind of a niche machine, and then I'll talk about what data we collect there and how we analyze it, and then some reflections at the end. So the premise here is that X-rays are really useful for science. Because they have a wavelength that's much smaller than visible light, we can look and interact with objects that are not directly probable with visible light, because otherwise we'd be hit with a diffraction limit. And initially, X-rays were, well, X-rays for science actually came out of high energy physics. So back in like the 50s and the 60s, when people were building particle accelerators, you know, these circular accelerators with accelerating magnets, people found that those produced X-ray radiation. And over time, people found more use cases for this and eventually started making purpose-built facilities called light sources, which are designed to just produce X-ray radiation. And the applications here are in many, many different fields. So there's solid-state physics, there's biology. A very famous example is single crystal, serial femtosecond crystallography. But there's a lot. So if you want to make radiation, all you have to do is accelerate an electron to relativistic speeds and then accelerate it in some way. This will get you radiation. And by tuning the amount of acceleration or the bending that the electron experiences and the speed and the electron velocity, you can tune the wavelength of the radiation that you get. So bending an electron means radiation. But we want to make more radiation, right? So if we want to make more radiation, then we just need more bends. And that's where undulators come in. Undulators are a series of magnets with opposing polarities. So north-south, north-south, north-south. And when you put an electron between these series of magnets, it will bend, and that will create even more radiation than just a single bend, right? This is a picture that I took. This is one of XFEL's undulators. In this state, it's currently wide open. So this is the top row of magnets, and this is the bottom. And this silver thing here is the flight tube for the electron. So in operation, those two magnet series will be closed together to give the maximum magnetic field for the electrons. This is also how synchrotrons work, right? So we have these circular particle accelerators, and then there are undulators that take the electrons and produce radiation. But back in, I want to say the 80s and the 90s, people figured out that there is a different regime that you could get into where we produce many orders of magnitudes more X-rays. And this is based on a principle called SASA, which stands for self-amplified spontaneous emission. The idea is that inside of your undulator, when you're sending an electron cloud through it, this is like a roughly homogeneous cloud of electrons, right? But in certain conditions, if conditions are right, then as this electron cloud passes through the undulator and it starts emitting radiation, that radiation will start to interfere with the other electrons in the cloud. This is the self-amplified part. And so this feedback effect means that the electrons start to order themselves, and they have what's called a micro bunching. And in this scenario, all of the electrons are now emitting radiation in phase with each other, which means that we can get many orders of magnitude more photons than you could with a synchrotron. And that's the difference between a free electron laser versus a synchrotron. This is the one that I work at. This is the European XFEL. On the right-hand side here is the site at DZ, which is also where Graham works. This is where the electron gun is. So the electron gun is a thing that produces these electron bunches. It goes into this linear accelerator. Here you can see a picture of the superconducting cryo modules that accelerate the electrons. And then all the way over here, the electrons pass through the undulators. So they go through here, they produce the radiation, and then we dump the electrons, and we keep the X-rays, and they go into the experiment hutches, which is where the scientists have set up the instruments and the samples. And this last bit over here, where the X-rays are, that's where I work. So these are another few pictures of the accelerator. Yeah, so I work at the very end of this. My job is to work with the instrument scientists and the users to help them analyze the data that they collect here. Most of the data arrives in what we call trains. So the X-rays that are produced arrive in these trains or macro pulses. So 10 times a second, there is a burst of X-rays in one of these trains. And within these trains, there are many different pulses. At XFEL's highest repetition rate, which is 4.5 megahertz, then you can get down to 220 nanoseconds between X-ray pulses. And the length of each pulse is something on the order of 20 femtoseconds. Though currently there are also some special modes where we can even get down to attosecond pulses. So it's very bursty, right? It's not continuous. And that means that between this train arriving and this other train arriving, we have to try and analyze that data. So our time budget per train is about 100 milliseconds. And we do produce quite a lot of data. The hardware that we use is very heterogeneous. So there's 2D detectors. Some of them are what's called pulse resolved, which means that they can distinguish those individual pulses within a train. And those can take thousands of images per second, so something on the order of tens of gigabytes per second. And then there are 1D detectors, so you might have like a digitizer that's hooked up to some diode, which you might use as some normalization signal. And then there's stuff like motors, which is relatively small. So most of the data is coming from these 2D detectors. This is one of them. It's 4 quadrants that can be moved independently. If you're wondering why there's separate quadrants instead of like a regular pixel detector, like a CCD detector you would find in a camera, the reason is because this is designed to let the beam go through. The X-ray beam is so powerful that if it directly hit one of these pixels, then the detector would explode, or it would be very bad. So this is what the control hutch of one of the instruments looks like. So this is where the users will be sitting during an experiment and running it. An experiment at XFEL is typically about a week, or sometimes even less, and it's kind of an intense experience because beam time at XFELs is quite difficult to get. There are many competing proposals. And so the users who come here will have spent potentially many months configuring their sample. They will be preparing different analysis things. They will be possibly preparing their own equipment that they bring. And it's really important for them to get feedback quickly because they really only have a small amount of time to do the experiment. And this is where online analysis comes in. So in photon science, there is this distinction between, well, we have this distinction between online analysis and offline analysis. When I say online analysis, that's essentially real-time analysis, but it's not real-time in the sense of like a real-time operating system, right? Real-time in this case means something happens and you see it in your results in a few seconds, right? And then after you've taken some data, you see some results online, you take the data, then all of this is saved, and then you can do what's called offline analysis, which is where you're just reading stuff from files and doing the analysis there. The goal is ideally to move as much of this offline analysis to running online, because this gives the scientists much better feedback. And this is this is a diagram that shows what the online analysis infrastructure looks like. So inside of the control system, there are different devices that represent hardware like detectors or digitizers or motors, and these are producing data that can be read by our analysis tools. The data is also sent to the data acquisition system. This is the thing that's writing stuff to files. And we also send detector data to our online calibration pipeline. For the big detectors, this is running on GPUs, and it's split across 4 nodes for performance. But we can intercept this calibrated detector data along with just regular digitizers or whatever, and feed it into our online analysis tools for quick feedback. And we already have some online analysis tools. And my motivation for working on a different approach to doing online analysis is mostly performance. The GIL in Python means that it's very difficult to get good performance without doing something like multiprocessing, which is what we already do. And multiprocessing is kind of annoying to work with, because once you have one process, you usually have to send some data, like some processed big array, to another process to do something else. And that has its own overhead. So I really wanted a system where we could easily use threads and access data that's in shared memory very easily. Another reason is good offline analysis support. So like I said, there is this distinction between online and offline analysis, and often the code that you run offline is different from what you run online. And this is annoying because it means that you have to implement the same thing twice. And it also means that you're not seeing, in some cases, the same thing online and offline. So I wanted something that you could run online and offline without really having to worry about where the data is coming from. And finally, I wanted a really good user interface. It's like operating an experiment is very complicated. There are, in some cases, hundreds of different devices and things that you have to keep track of. And without a good interface, you just lose track of what's actually happening in the system. So that led me to working on this thing called XFA. It's a framework for doing streaming analysis. I don't say it's specifically online or offline analysis, it's just streaming. So you can stream stuff from online data, or you can stream stuff from offline files. And to build your analysis pipeline, you can write code, just regular Julia code inside what we call a context file. You give this thing to the framework, and it will execute that for you. So it will take care of getting the data from the control system, passing it to the functions, handling buffering and errors and that sort of thing. A very important function of the framework is a thing called train matching. So every bit of data coming from the control system has what's called a train ID, which is a unique identifier for it. It's kind of like a timestamp. And if you try and compare data from different timestamps, you will get completely rubbish results. So this is a very important function. The architecture is, I think, fairly straightforward. There is an engine, which is like a server backend thing that's running on the online cluster where the control system is running. And this is what's loading the user's context file. It builds the DAG, and it streams in the data in and runs these functions and produces some outputs. When the outputs are produced, it will send these to any listening clients. So the client in this case is a native GUI. It connects to the engine over SSH with port forwarding. This is just the simplest way to do it. There is a graphical node editor to edit the pipeline, and there's a bunch of options for plotting and so on. And all the communication between the engine and the client is done over WebSockets. A bit more details. I think the main things that I want to point out is that we use ZFP for compressing the results before sending them from the engine to the client. This is quite important because the client might be like me running the GUI on my laptop from home to debug something happening over there, and you can quite easily be streaming like tens of megabytes per second over a residential network, which is sometimes okay, but also sometimes not. So this is really important. The client is written using Dear mGUI and implot.jl. So that's an immediate mode user interface. We try and take advantage of labeled arrays from dimensional data where possible. So that gives us things like plot axes and named dimensions and that kind of thing. The SSH stuff is all done through libssh.jl. And the GUI is multi-threaded. So there is one task running on one thread that just does the event loop. And then there's another task for handling decompression and reading data from the engine and so on. You can also edit the context file from the GUI itself, and that's done using Julia syntax. So Julia syntax provides a concrete syntax tree, and that was actually amazing to use. It's super cool. This is a quick example of a context file. So what we're defining in here is regular functions that also have like a bit of a domain-specific language. So these functions are annotated with this variable macro that tells the engine that this is like a variable that should be run from stream data. And it says that this particular argument is coming from this particular device in our control system. And then inside here, you can do whatever you want. In this case, it's just returning the array. You can also group variables together. So in this case, we have a group that is just a struct, and it has a couple of parameters. And you can define functions on that group, or variables of that group, that will use the parameters in here to do some kind of analysis. This is really useful for reusing code. And that's just an example of instantiating the group. I'm not particularly wedded or really happy with the syntax yet, so this may change in the future, but that's what it looks like right now. Now, I was going to do a live demo. Unfortunately, I cannot access the DZ network from the university Wi-Fi, so that's not going to work. But I did anticipate this, and I took a screen recording instead. So we'll have a look at that. Here we go. So maybe I will slow this down and just go bit by bit. So this is what an example context looks like. Let's see if I can zoom this in. No, I don't think I can, unfortunately. Never mind. Oh, and I think VOC just crashed. That's devastating. Okay, let me open this again. There we go. Okay, so this is the node graph. This is the GUI is all written with the Dear mGUI. You can scroll and browse around the graph. Each box here represents one of those variables that we saw before. Let me pause this and maybe go back over here. The outputs that you can see are things that are returned from the function. In some cases, you can see that there are multiple outputs. Those are things called subvariables, which is another thing you can define in the context file. Visually, you can see that there are lines connecting the nodes, and that just denotes like which bit of data is going to which other function in your DAG. So yeah, I think we can continue. This is just a regular image plot. This data is also being compressed, by the way, and it's super effective, I think. So in this case, let me just go back. This is reducing the amount of data sent to the client by 6 times with, as far as I can see, almost no visual artifacts, which is quite nice. this is what a regular line plot looks like. This, I think, is just the variance of a region of interest on that camera. There's some simple plotting options like displaying the plot in log scale along the axes. And you can also select arbitrary scalar or vector sources and correlate them versus each other. This is really important, actually. Like half of the analysis that people do online is all correlations. Binning is also supported, so here you can see that we're binning things within a certain resolution. This is useful for doing scans, and you can also fit some simple curves to this. And I think that is almost everything. Okay, there is one more thing here. You can see that I'm dragging a link from this socket to this socket of the other node, and it kind of reconfigures itself. Internally, that is using Julia syntax to modify the context file and then reload it. And that's how the editing from the GUI works, which is quite nice. So that's the demo. I also prepared some pretty pictures since the demo won't work, or live at least. Most of the time, the pulses that we get at XFL are on the order of femtoseconds, as I said before. We are also doing a lot of attosecond research these days. When you look at an XFL pulse with a spectrometer, it usually looks like kind of bell-shaped, like a Gaussian. When you get attosecond pulses, that Gaussian kind of decomposes into multiple Gaussians, and you end up with these spikes. And one way of getting an estimate of the pulse length is by fitting curves to these spikes and counting how many of them there are, and also the width of them, and so on. So this is one example of using XFA to do spectrometer analysis for an attosecond experiment. This is actually from a few months ago. Here the users were doing single crystal diffraction. What you see on the left-hand side is what's called a Bragg peak. So this is a reflection of X-rays from a crystal, and there's some really nice diffraction fringes going on here. Later on, the users will use that for reconstruction, so they can actually use this data to reconstruct the original crystal. And here's another example of looking at a Bragg peak. In this case, the thing that I want to point out is that we have what's called a pumped image over here and a unpumped one over here, and you can see that there's a difference between them. That difference is what we're looking for. That's like the signal that we're plotting. This is a delay scan, so we're plotting the intensity of some region of interest versus some time delay as we're scanning through it. And later on, the scientists would use this to figure out what the sample is doing. A few quick reflections. So as someone who writes the code for these experiments, I love having fast access to a fast language. Being able to multi-thread things so easily is really amazing. There are some power users, I would say, some scientists who are good at coding and want to write their own code. And I will say that having this context file written in Julia is a bit of a barrier for them. I think that the trade-off I made is in favor of the people who are mostly writing the code, people like me. And I hope that this won't be such a big deal as we add better support for Python and maybe even returning NumPy arrays from variables. But it is a trade-off nonetheless. The GUI, I think, is the thing that's most appreciated by the scientists because it's very reactive. It's fluid, it's smooth. You can view stuff at 10 hertz. Plotting is really nice. And this is really enabled by a combination of Julia for the multi-threaded GUI client and also mGUI itself, which is just a great framework for this kind of thing. There are a bunch of future plans. I think I won't go over most of these for the sake of time. One thing that I will point out is using revise.jl for handling changes to the context file. So right now, if you change the context file by editing it or by changing dependencies, like we saw in the demo, that file is reevaluated. And in theory, I designed this so that it's possible to use revise for this instead, which should be a bit lighter. And I think that would be very interesting to do. That's it. Thank you.
Thanks very much, James. So we have plenty of time for questions. I'll open it up. One over here.
Yeah, I was wondering about what you mentioned, that you edit the context files. Is that a performance optimization in some sense, or could you use some data structure which allows you to basically hook into it and say, okay, now use a different field instead of this field or something?
Yeah, I made the intentional decision to edit the context file instead of like using in-memory stores for things like parameters or connections between variables, because the context file kind of functions as a database. When you close when you close XFA and you open it again, I wanted it to be possible for like the previous state to just immediately show up. And one way is by maybe storing these settings in memory and saving them to a separate file. But I felt that it would be a bit cleaner to do this all inside the context file, and that's why I went for editing it with Julia syntax.
Thanks, James. More questions? We have one over there.
Yeah, I like the look of the GUI and the plotting and stuff. Since I'm developing Marquee, do you maybe have some experience also with GL Marquee GUIs, and can tell me like what the main thing you like about, or the main things you like about GUI are, so that we can kind of learn from them for the future?
Yeah. So I actually started out using GeoMarquee. I wrote the GeoMarquee integration with CMGUI. The reason I moved away from GeoMarquee was time to first X. It was a little bit painful to click the plot button and have to wait like 10 seconds. From the standpoint of features, I think Marquee is absolutely superior though. Like you can have, there's things like the observable system, which I think was actually refactored, but that kind of thing is much more powerful than anything mplot can do. And so in theory, I would really love to use GeoMarquee, but it didn't really fit for this particular thing because of time to first X.
Okay, more questions? Ooh. Good thing I didn't go all the way down the stairs then.
Thank you for the talk. How closely is your setup linked to your European XFL? And do you have any plans to make it available to other accelerators and maybe also integrated with frameworks like Epics or stuff like that, that do part of what you do already but don't have the nice presentation and adaptability?
It's fairly tied to XFL right now. It assumes things like train IDs exist, for example, for the sake of alignment. I think I'm open to the idea of making it work for other facilities, but I've had some experience with trying to make other programs like cross-facility before, and it's a very, very slow experience because you need buy-in from the people at the other facilities. So I'm open to it, but it's not something that I'm going to push, if you know what I mean, because that's a lot of work. Yeah.
Thanks. One last quick question. Okay, I don't see anything, so let's thank James again. And we'll move to the next talk. next talk is Max, and he's going to tell us about structural equation models, which sounds really fun. So I'll let you take it away, Max. Sorry?
Do you have a
work?
Okay,
Yeah,
I can do that.
So you can do a bit of pointing with that.
One more thing. Sorry. Yes, that looks good. Okay. Yes, my name is Maximilian. I'm a PhD student in Berlin at the Max Planck Institute for Human Development. And I want to present a package that I've been working on together with these lovely co-authors down there. And it's called Structural Equation Models. And it's a package for structural equation models. But since I assume that probably many of you are not very familiar with it, or maybe never even heard of it before, I give a quick introduction into what these models actually are. So structural equation models are a kind of statistical model, and I want to start with a very basic model, and then I will add stuff until we finally reach a structural equation model. Okay, so the basic model I want to start with is a simple linear regression. I guess all of you are familiar with this. You have two variables. One is the predictor x, and one is an outcome y, and you model y as a linear function of x and allow for some error term. And we can put this into a graphical depiction as shown on the right here. Predictor, linear factor, outcome, and your error term. Now, if you want to take it a step further, you can add another predictor. Then you arrive at multiple regression models where you model an outcome as the sum of linear functions of the predictors. Then, taking a bit of a bigger step to make it more complicated, you can allow for multiple outcomes, and then you can allow some outcomes to be an outcome and a predictor at the same time. And then you call these variables mediators, for example. Y1 here is predicted by two variables, but is itself also a predictor of another variable. And this is typically called path analysis. And one additional change that we make in introducing this possibility is that we also start to explicitly model undirected effects. So now we don't only have linear directed effects where one variable is a linear function of another. We also explicitly model which of our variables are allowed to share variance or to not be independent in our model, and we depict this with these undirected effects. And now we make one step further, and we are at structural equation models. So what we need to add still are so-called latent variables. Latent variables are variables that you want to model or you assume to play a role in your model, but you cannot directly observe them. So here, this eta is a latent variable, and since we cannot directly observe this variable, we have to measure it somehow. And here we measure it by these three variables, and this is pretty simple. So to make a very simple example, this eta might be the temperature in this room, and we have three thermometers, and all of these three thermometers are measuring our temperature, and some of them might be more accurate than others. So we have different error magnitudes, and they might be on a different scale. So one might be in Celsius, one might be in Fahrenheit, and this is what we can model with these linear effects. How do we estimate these parameters then? Well, there are many different possibilities. The most common one is the maximum likelihood approach, where you assume your variables to be normally distributed, and then your parameterization of the model gives you an implied covariance. So the covariance between the variables is a function of the model parameters, and this you can then compare to the observed covariance in your data and compute discrepancy between them, and then compute gradients, and with an iterative optimization approach, try to minimize the distance between the observed and the model implied covariance. Okay, So a small recap, structural equation models are networks of linearly related variables. They can include observed and latent variables, and parameters are typically estimated via numerical optimization. There are also variants of all of this, variants with nonlinear effects, variants with non-iterative optimizers, but this is the most common approach. Okay, I want to go through a few example applications. So this is basically my background, psychometrics. And here structural equation models are heavily used because you often try to model things that are not directly measurable. For example, you might be interested in the relationship between two psychological disorders like depression and anxiety. And then these disorders you measure via multiple symptoms. So you have something like quality of sleep and self-harming thoughts, for example. And in these settings, you don't know beforehand how much error you have in your measurements, and each of your symptoms might have a different amount of error, and you also don't know beforehand the scale of your measurements. So this is a very fitting approach for structural equation modeling. Then a second example. So here this is an example where we have multiple measurements of the same quantity. So we have 4 repeated measurements, and there's some structure to this measurement. So this is an example from an MRI study. And what we have here is 4 sessions, so 4 scans, but two scans each were performed on one day. So these 2 scans are performed on the first day, then there's a month break, and then there are 2 more measurements on another day. And what structural equation modeling allows us is to introduce some assumption into the modeling of this data. So here the assumption is, for example, there might be something like, okay, we have one MRI machine used on the first day and a different MRI machine on the second day, so they might have different error variances. So we can fix the error for the first 2 scans to be equal and then allow the error on the second day to be different because we use a different machine. And then we can also measure the fact that the measurements on one day might be closer to each other than the measurements a month apart. And in the end, we can extract a stable component over all 4 measurements, and we can then use this stable component to predict something that we are interested in. And this is also a very interesting use case for our package, because these MRI scans, they usually measure your quantity of interest in these small cubes in your brain. They are typically called voxels, and you might have something like 1 million voxels, and then you might want to have an estimate of your quantity that you're interested in for each voxel, and this means that you have to fit 1 million models. And for these kind of applications, you really benefit from having a fast software solution to do that. So the last example that I want to make is from the field of genetic epidemiology, and this is basically a very classical model that I depicted here that can be used to estimate the heritability of traits. Here you have a so-called twin study or twin design where you have monozygotic and dizygotic twin pairs, and you have some trait that you measure in each twin, and then you want to basically disentangle how much of this trait is heritable and how much of this trait is determined by the environment. And this is an interesting use case for structural equation modeling because here you have 2 different groups. And the way this kind of study design works is that you need these 2 groups with different properties, and you need to fit your model simultaneously to both of those groups, the monozygotic and dizygotic twins. And what structural equation modeling allows you is to do that and to basically decide for each of your model parameters whether this is a model parameter that should be equal across groups or whether you want to allow this model parameter to be different. So for example, you might be assuming that the general effect that you want to estimate is equal between the groups, but for example, allow for different measurement error between the groups. Okay. Now, I hope this was okay, very quick, but maybe hopefully understandable introduction of structural equation modeling. So now I want to come to our package, structural equation models. So why writing a Julia package for this? Well, I guess it's a bit of the story of every Julia package ever. Using Julia allows us to write a package that is both very extensible, so we have everything in one language, we have a nice type system, we have multiple dispatch, so we can make it very easy for users to add new features to the package. And at the same time, it's very fast. How do you specify models in our package? Well, this is basically inspired by Lavan, which is a structural equation modeling package written in R, which has this very nice graph specification syntax. And one of our co-authors, Aaron, he decided to write a Julia package for this, a small standalone package called stenographs. And it's a package that just provides you with this stenograph macro that allows you to specify graphs very easily and in a relatively human-readable form. And it also allows for all kinds of things that we need in our structural equation modeling package. For example, you can attach modifiers to the edges, and this allows you, for example, to encode model constraints, it allows you to label edges, it allows you to fix edges to certain numbers. This is what we use for model specification. And the implementation then basically consists of a set of abstract types. So the model itself is of type Them, and then each Them can consist of one or multiple loss terms. So if you have multiple groups, for example, you have more than one loss term. And then each loss term, again, can host a Them observed type. And this Them observed type basically takes the observed data set and does some pre-processing to allow for efficient optimization then. And then you have this Them implied type, which takes your model parameters and computes model implied statistics. And then you have this loss type, which brings those two together and computes a loss from them. And what Julia allows us is to have all of this very modular, because we can tell and we document that, okay, if you want to add a new loss term to our package, what you have to do is you have to implement a subtype of some loss, and you have to provide methods for certain functions. And if you do that, you're good to go, right? You don't have to understand any other code in our package. You don't have to understand what happens inside the other types that you're using. You just have to follow our instructions and implement certain methods. And this is what multiple dispatch allows us to do. And then last but not least, we also have the optimizer, which then connects to an optimization backend. And having this in Julia also allows us to leverage the amazing package of ecosystem of Julia packages. So for example, we have multiple optimization backends that we can let users use. Per default, we use Optim with a quasi-Newton method, which is written purely in Julia. Then we also allow to use NLOpt for more complex nonlinear constraints. Or we can also let users use more like recent or cutting-edge optimization algorithms that are difficult to find outside of the Julia ecosystem, like proximal algorithms, for example. And we can provide features that no other structural equation modeling package has currently, like optimizing with non-smooth terms, such as L0 regularization, for example. What we can also do is we can use Julia to speed up our computation. So one really exciting and cool thing that we are doing is we are using symbolics and sparse arrays in combination to basically trace operations symbolically through some sparse matrix operations that we have to perform at each optimization step. And then instead of doing these sparse matrix operations again and again, we trace them once with symbolics, and then we generate a function that basically just computes the outcome of these matrix operations. And this allows us to have quite a speed up in optimization performance. All right, so the last thing that I want to show you are some benchmarks. So here we compare against the two most widely used structural equation modeling packages. The first one is Lavan, it's an R package, and the second one is OpenMX, which has a front end written in R, but all the compute-intensive tasks, such as the numerical optimization, are carried out in C++. And we compared all three packages with the standard optimizer settings. And this is the model that we use. It's a fairly standard structural equation model. And what we do is we vary the number of factors, and we vary the number of indicators per factor, so the number of parameters is varied. And here on the x-axis, we have then the model size, or the number of parameters, and on the y-axis, the time it takes to fit a model in seconds. And we can see that we can achieve quite a speed up over the other packages. So the bottom two lines here are Zem.jl, and the lowest line is the variant that also uses the symbolic precomputations that I talked about. And we can see that we are quite a bit faster, 2 orders of magnitude, especially for small models. And then as the models get bigger, we basically have this phenomenon that more and more of the computation time is actually spent in the linear algebra backends, in the class libraries, basically. And since we fix all of the packages to OpenClass in this example, then the performance difference gets smaller. Okay, so in Outlook, what are our plans with the package? So first of all, our package is limited in features at the moment compared to the more mature packages out there. They have quite some development time already in, and quite a bit larger feature set than we have. Something that we would like to add is support for ordinal data and support for multi-level models. If you have nested data structures, for example, then something that we are also working on are performance improvements for larger models. So we have some ideas how to incorporate the sparsity structure that we find in many large models to allow for more efficient model fitting. Something that we are also working on is a little add-on package called voxel-wise Zem, and this is basically a helper package for these voxel-wise MRI analyses that I talked about a little bit. Yeah, because this is an application where you really fit many models, and that can really benefit from our package's speed. And the second point that we are working on is improving support for automatic differentiation. Yes, and check us out on GitHub if you want, and that's it.
Okay, that was a very interesting talk about new package. So we're open for questions now. What would people like to ask?
Thanks very much. I have a kind of more mathematical question in a sense. I was wondering how much does it limit you to have only linear relationship between your variables?
Yes, thank you. I mean, that's a very general question. I think that really depends on where you apply your model. I think there are many applications where this makes total sense, and it's very usable, especially if you have these latent variables that you can only measure indirectly. There are some approaches that incorporate nonlinear effects into structural equation modeling. We don't have them in our package yet, but there is an option to do that. But yeah, I think in general, it really depends what your subject matter is. If you have highly nonlinear effects, then I think it's just not the right modeling tool. Yeah.
Okay, other questions? We're over here.
Yes, thanks for the talk. I was wondering, why do you need autodiff if everything is linear, essentially? And if you do, what are the challenges there?
Sorry, can you repeat the first part of it?
Why do you need autodiff if essentially everything is linear? So what kind of functions would you get the gradients of?
Yeah, that's a good question. So the effects between the variables are linear, but the model implied statistics, like the model implied covariance matrix, is highly nonlinear. So even if your effects are linear, it doesn't mean that the loss function that you optimize in the end is linear. And what you basically get, I mean, I can go a little bit more into the details. What you basically get is, I think maybe this is a good example. So what you basically get is, if you have this normality assumption and then you want to compute the covariance between y1 and y2, for example, what you will get is the product term between the two linear effects, beta 1 and beta 2. And the larger your model gets, the more complicated these product terms basically get. Yeah.
Thanks. Do you have another question? Yes, we do.
Thanks. I wanted to ask a question in continuation to the other one. You mentioned that you're tracing here with symbolics.jl. Would that also help with the AD question, essentially, by doing it symbolically?
Yes, that's a good question. So, yeah, what we do is, in the case where we trace computations with symbolics, then we also use symbolics to compute the derivatives symbolically, and then we compile a function that computes the derivatives, right? But where the problems basically start is, or what we didn't find a good solution for yet is if we allow a user to add their own types, and then the user wants to mix and match types with ours, and then they want to automatically differentiate all of that. And then we run into the problem that the specialized and performant code that we wrote is not automatically differentiable. So I'm not sure what the best way forward is. If the best way is to just say, okay, we implement a chain rule for all of our types, and autodiff never really looks into what the code that we have written, or if we should write our code in a way that the backends can actually differentiate through it. And I think this is basically the question.
So the problem with the user-given code is that it might not be differentiable by symbolics. Like, do the users need to register their struct or something like that?
No, the problem is more that our code is not differentiable because we use things such as mutating arrays and so on. So we use features of the Julia language that for many optimization backends are not differentiable. So we would need to adapt our code so it's differentiable in conjunction with some code that the user has written. Mm-hmm. Does that make sense?
Yeah. I thought that it was like fully symbolic, and that's why I was thinking that. Yeah.
No, it's not fully symbolic.
Okay,
no.
Thanks.
Okay, we still, got another question. We have time, so let's go.
So what about item response theory? Can I fit these types of models with your package? And kind of related, then maybe I would want to use another type of estimation. So is that, or will that be supported, or is that supported?
Yeah, I think this is basically the number, one of the two most common feature requests, item response theory and multi-level models, and these are the two things that we are working on at the moment to support, yeah. But at the moment, it's not in there yet.
Okay. Maybe I will ask a question about performance, because you showed some really impressive numbers, which was great. And I'm just wondering, in practical use, when users are using these type of structural equations, is this a pain point? Because if the other codes run in a couple of seconds, it's probably good enough. There's not a lot of incentive to change. If, on the other hand, it's taking 10 minutes, an hour, then people actually suffer from the performance. So in general, for these kind of problems, where are users?
Yeah, it's an excellent question. So I would say for the average applied researcher fitting a fairly small model, it's not a pain point. And I think there's also not a very big incentive to then change to our package. I think the kind of users that we want to address are users that either fit many models in parallel because they are doing methods research and they want to improve the method itself, where this is very common, or they have an application such as I showed with the MRI analysis. And then the second application, and this is something that one of our co-authors, Alexi, is doing, is applications where you really have thousands of variables. And this is something that we still want to improve, but already now, if you have a very big system of variables, even though the performance difference shrinks, I don't think that it's really viable to fit these kinds of models with any other package because they just take too long or they take so much memory that it's really not feasible anymore. So basically, fitting many small models in parallel or fitting very big models are the points that we want to address.
Yeah, so you've got a target audience, really.
Yeah, definitely, yeah.
Pain always helps with migration. Okay. Any last quick questions? No, I think not. So let's thank Maximilian again. Okay, and we'll get set up for the next speaker, who is Marco. Our next speaker is Marco, who's going to tell us about symbolic post-hoc analysis. So off you go, Marco.
Okay, hi guys, I'm Marco Perrotta. I'm a master student in the University of Ferrara, and I'm collaborating with the Acclay Laboratory, and today I will talk about symbolic post-hoc analysis, one part of our framework, SOLE.jl. We already present SOLE.jl in a lot of JuliaCon, JuliaCon 2023, 2024, and 2025. This is a different part, but in every we study the symbolic learning, the good old-fashioned artificial intelligence. Okay, what is it? This study the algorithm that produce model expressible and logical rule, for example, decision tree, decision list, or decision forest. Was prediction can be traced back to human readable condition in input data. Okay, you can see why one model classify one specific label. This is the main idea. This is one example of a classical machine learning pipeline in SOLE.jl. You can see, and if you are curious about that, you can talk with us in the poster session where Paso, Dr. Paso, hi Paso, talk about that. But into general, we can start with the raw tabular or non-tabular data, and with this, we can extract a logset, one representation, one logical representation of this data. With this, you can learn a lot of type of model, of symbolic model, with the solo learning. Okay, this is the idea. And after that, only once a model exists, can post-hoc analysis begin. This is the idea of Sole post-hoc. With Sole post-hoc, you can do a lot of things, a lot of for post-processing stage, okay? This is the most relevant insight about one model. Why we can start? We can learn one model. To demonstrate Sole post-hoc, we first need to train a symbolic model. Exists a lot of package, lot of standard in Julia community, for example, MLJ or decision tree. In this case, we can talk about our package, but it's not this the focus, okay, of us. And for this reason, we prefer use one own method. In this case, we can extract the logset by one dataset, for example, one toys dataset iris, and after that, learn with one method, learn what we want to learn, one forest with the 5 trees. This is more simple, and you can see this model. Maybe you can translate another type of model, but it's not this the focus. Okay. After that, we can start with Sole postdoc. What we can do with postdoc? We can do a lot of things. For example, we can do one rule extraction, okay? Why you won't do one rule extraction? Okay, you can see the model, but you don't know why one model classify one rule. Okay, you know you can put one instances and this classify iris setosa, but you don't know if and why this is iris setosa. This is with 5 trees, but with 100 of these is very, very difficult. For this reason, you can extract the rule for classify one label, okay, label by label, obviously. Many algorithms exist, yeah, but the complexity of this is very difficult and depends on one characteristic, one feature about that. You want to enhance these capabilities, for example, the depth or the size of the forest. In this case, you can do one ensemble compression, okay, and the ensemble certification. For example, you can certify one model for any constraint. For example, you know exists one type of flower, and you can create this constraint if it's not already satisfied by your model. Okay, we can start with the rule extraction. Rule extraction, the goal is deriving explicit interpretable logical rule from training symbolic model that explain the decision process. With Sole postdoc, we have a lot of two main approach for do it. We have a lot of algorithm, yeah, but the first approach is to call directly specific algorithm function. This is one example. This is not all our method, but it's the most famous or most classical method for rule extraction. In this case, you can extract with InTrees or Beatrice, RefNet, Trepan, or Lumen. Okay. Notice that this approach returns the output in original format defined by the algorithm, and you have to call this with his name, his argument. This is good, okay, but this is one example where InTrees, for do InTrees, you can call it, and after that you return one decision list. What is a decision list? A decision list is one list of rules, okay, where if it's not true the first, you can try the second. If it's not true the second, you can try the third, etc., etc. Okay, good for InTrees, but with ref no Beatrice, you return a surrogate tree, another type of model, okay, one trees, and with the Lumen, you return one decision set. This is for the first approach. It's good, it's okay for all, but it's not the second approach, my favorite approach, where you can use a field interface through the rule extractor. You can create one rule extractor, for example, Beatrice rule extractor or Lumen rule extractor. Input here, you can put a lot of argument, okay? And after that, put this rule extractor in extract rules, our method, one interface. This package primarily proposes into general Sole, okay, framework case to provide a unimore interface for knowledge extraction algorithm and for all our algorithm. In this case, different algorithm, the different output algorithm is in one type of this. This is one decision set where you have one DNF, okay, for any rule. For example, for the first rule, you have only one. For the first label, you have one rule, and you have one only rules. And for the second, for iris vesetosa and for iris virginica. This is the second approach. Okay, you can extract the notion. Now, a lot of these methods use a different, have a different complexity about that, okay? For this reason, maybe you want to enhance the model capability by boosting performance on specific metrics, such as size or depth, or in this case, we do it in either this, okay, in the same moment, you want to enhance the size and the depth about our model. This is one example of this. In this case, we use, you can do it through the proprietary compression algorithm, okay? In this case, we can call compression with the Sole forest, the size or the characteristic, the feature what you want to enhance, and after that, you can call here. This is one example of genetic algorithm in our package, but yeah, this is. And with this, you can create uncompressed models. Okay. After that, we talk about rule extraction. We can talk about the compression, okay, the compression, but we can certificate our model. Okay, we can certify our model, sorry. In this case, why you won't do it? You want maybe to guarantee the satisfiability of this related feature of constraint over the model, expressed as a formula in propositional logic over its scalar condition. Into really, you can use some different logics, for example, modal logics or fuzzy logics. If you are interested about the logic, tomorrow we talk about that with Alberto. But into general, you can create one constraint, and after that, certify your model if check and certify your model. Okay, this is very interesting point for this case, because in this moment you can imagine one pipeline where, for example, one person, one doctor, for example, Dr. Polo, okay, Mr. Polo, can create, he is a master of the iris, okay, iris dataset, and he learn one random forest. In this case, he'll learn one random forest with 100 of trees, and after that, can try to do one rule extraction. Okay, he try lumen, for example, but lumen depends on, the complexity of lumen depends on the number of the trees, and the depth and the alphabet. In this case, he try lumen, lumen failed, but after that, he can try to use one compressed method, one compression method for compress in these capabilities, and after that he obtain one compressed method. Okay, now we have one compressed method. If you are interested, this is the paper, but just work, and 100 of trees is he transformed it, compressed it in 20 trees, and after that you can try to rule extraction, one rule extraction. You can try to extract the rules, and after you see the rules, okay, the model is okay, the accuracy is 100%, okay, percent is very, very good, but he noticed that one feature don't exist in these rules. Okay, he is a professional, he knows about that, and for this reason, he creates one constraint. For example, this constraint is pattern length greater than 672 and pattern length less than 688, etc., etc. After that, can put this constraint in the certify method and put our Sole Forest, him Sole Forest, the constraint, and create uncertified model. This is one example of pipeline, but we study it with different logic. This is in propositional logics. You can try to catch the temporal logic and use it. This is possible under now, and yeah, it's so fun to use it. For conclusion, the core premise of about our package, post-hoc analysis where symbolic learning relies on tuning a trained model into usable, understandable knowledge, okay? And Sole post-hoc is a reliable, extendable toolkit for interpretability, explainability, and model manipulation. If you know, do you like it, and you want to try and collaborate with us, this is an open source package, okay? It's a long-term open source project, and if you want to collaborate with us, you are welcome, and thank you for your attention.
Thank you, Marco. Okay, so we have plenty of time for questions. I'd like to ask something. Maybe I'll just start off while other people think. So I was just wondering, the users of this package, obviously, you know, everybody is obsessed with LLMs and neural networks these days, which are much harder to interpret. Is the main goal here not to get the highest ACU, but to have a model which you can interpret? Is
okay,
that
yeah,
the motivations?
With our package, you can interpret this type of model, and you can study it. It's not our focus, okay, under now, but with all surrogate method, distillation method, we can do it, and we study how we can do it. Yeah. We study it. Our laboratory study the symbolic learning and not the neurosymbolic or deep learning, but exists. One part of our laboratory can start with this, and our focus in the future maybe is here. Yeah, thank you.
Okay, thanks. Still time for a question or two if people would like to ask. Okay, I'm not seeing anything. So anyway, then thank you again, Marco, very much for the talk. Appreciated it. And we'll go to the last talk of the session. Of this session, which is Sebastian, who's going to tell us about Bayesian model calibration using Turing. So somehow we've come full circle to the next talk about Turing to finish up. Take it away.
Talk on Bayesian model calibration using Turing, and particularly I'll focus on how we did the parallelization on CPU and what we achieved on GPU so far and what we are still fighting with. Maybe for the few people that are still sitting in the same room as 1 hour ago, our primary application is also particle accelerators, but since the framework is problem independent mostly, I didn't reference a lot to it. So, a short overview, I'll give you a short introduction on the Bayesian calibration and what we do there, and then I'll go into more detail on the modeling in Turing. Exactly. So first of all, the model calibration, the idea is that we basically have two pathways to our output variables in our case. We usually have an experiment. In our concrete application, it's a particle accelerator where you have inputs and they are projected on some output that you can measure. But to prepare such an experiment, especially nowadays, you always also have simulations. And you use those simulations to, first of all, plan your experiment, and second of all, also to deeper understand what's actually happening in the experiment. And in the simulation, you have the tweak that usually you have to calibrate your simulation to your concrete experiment. And there's usually a whole host of parameters theta that you have to know next to your input to produce a concrete output. Z or zeta, depending on which. So in the concrete case, the idea is that we basically generate data sets for both of these. We generate a simulation data set, which is very straightforward. We just sample a certain region of input parameters and parameters, and for the experiment, we run a few experiments. One thing to mention here is that usually we have a very strong imbalance. The experimental data is a lot more expensive to get than the simulation data, so we have a lot more simulation data and very little experimental data. And the idea of the whole exercise is then afterwards is to get the posterior distribution, here just some fictitious function, where we would like to see how these input parameters are actually most likely distributed. Especially would also like to find out if it's maybe multimodal, so that our experiment actually has two settings where it falls in depending on some maybe not well-controlled external variable, so that we can actually understand what to do and we don't just want the most likelihood estimation. Yes, so as I already said, we have different kind of quantities of interest, and we are in the end interested in the distribution of theta. We do this using a Gaussian process. The main idea of the Gaussian process is that you have those black dots, which are basically the known points, and the Gaussian process gives you a prediction, what it thinks will happen, a mean prediction, which is the black line, but in addition it also gives you an uncertainty range, basically telling you how likely this output diverging from the black line can still be. We use this basically Monte Carlo sampling our parameters that we're interested in. So you try out a parameter, and the line at the bottom here gives you the log likelihood that this parameter is compatible with your experimental output. You have a lot of choices usually in the Gaussian process. You can choose your kernel function first of all, and the hyperparameters of the kernel functions, which here's the gram matrix K. And in the fully Bayesian context, you would like to be able to change those during the sampling, and in our case, we would at least be able to change those between experiments, so we can change some settings. Yes. So why we like Turing to do that? Turing is very, very convenient to just using a few packages, we can describe our model, and it is also very feasible to change this model depending on your application. So if in the experiment we choose to measure a different output, we choose to include another latent variable that we like to control for, or introduce an additional error. This is basically an additional line here where you see on the top where we started defining the distribution that our hyperparameters follow. You can just similarly introduce a new epsilon, tilde, tell it what distribution it is without changing a lot about the rest of the system. Maybe going through the code, basically for our model we describe the priors for our hyperparameters. Then we describe the distribution of the parameter that we are trying to infer. We construct our sigma, which is the gram matrix, and then we calculate the likelihood for a sample. So the question is now, we would like to parallelize that, and how do we parallelize that? First of all, it's very convenient for us that at least the auto-forward diff in Julia is compatible with the add threads, so it's very easy to loop over certain variables and distribute them on different cores. We also tested it for auto-reverse diff. It would break the add threads, but it was slower anyway in the range of parameters that we are considering, which are way below 200 or maybe up to 200, but not higher. So we didn't invest a lot of time in there. But there's still a question of what can we actually parallelize in the problem. The main workhorse of the Gaussian process is the gram matrix, which you need to invert or use the Cholesky decomposition of that, which is not trivially to parallelize. And then there's the question, how can you actually make use of multiple cores? First of all, there's a very straightforward thing that you can parallelize. Often you don't, in your experiment, in your simulation, you don't have only just one measurement, but you measure multiple outputs, so you can in parallel check one parameter against multiple output functions, which are easy to parallelize. Here in the for loop, this is the n-res over which we loop, which is the R. And second of all, we use the idea of the Bayesian committee machine, which you can use to break up your Gaussian process under a few assumptions into smaller Gaussian processes, which are then, you can loop over those smaller Gaussian processes, which don't only have an impact or an advantage because you now have things in parallel on different CPUs, but also the inversion or the Cholesky decomposition of those smaller Gaussian processes is faster. So here you see the mathematical formula and mathematical idea because behind the Bayesian committee. So basically you decompose the log probability of your Gaussian process of trying one theta into multiple of those, and this gets you around the O(n) to the power of 3 growth that you would expect from larger and larger Gaussian processes, and you can basically afterwards just multiply those probabilities or sum if you're in the log probability space, and you would still have the small correction factor, but apart from that, it's straightforward to adapt to your original model. So we tried that. The idea of the Bayesian committee is a bit older, but not used so much. We tried it, and here you can see how our simulation behaves, our calibration or inference behaves for different number of breakups of data set splits. So we have the blue line, which is the original, so to say. We don't split up our simulation data set, but we just keep it at one big set. This grows quite fast, and then already only splitting it up into 2 separate simulation data sets for which we infer basically independently or at the same time, we get an improvement, and going down to splitting it up to 8 cores, which is quite reasonable even on most laptops, we get a nice speed up. And yeah, we implemented that and recently got accepted. So we get a speed up of almost 16 times, which shows that we don't just capture the speed up of using 2 cores at the same time, or 8 cores in this case at the same time, but also have speed up in the numerics. Yes. So as a small recap in the middle, we try to find the posterior distribution of our parameters such that they are conditioned on the simulation data and the experimental data. We model this in Turing.jl because we want a very flexible model that's easy to adapt, where we also can use a whole list, a whole host of different solvers or samplers. And we use the Bayesian committee machine idea to speed up the Gaussian process and to also parallelize it in the same thing. And the nice thing about the Bayesian committee machine is that it's pretty problem agnostic and it only cares about how much you can split up your data sets. And we found that there's no problem with regards to errors if your individual committee members get still enough data. So of course, if you put it ad absurdum and starve the committee members of data and each of them just gets a single data point, then you see that there's a problem. In our cases, we saw that the problems are if each of the members gets less than 20 data points. So we usually gave them 100 and didn't have a big problem, but still were able to perform our stuff on the data sets of 5,000 samples. So yes, and we keep all the flexibility, which is very nice. So I told you that we also try to put it on a GPU. For a GPU, usually there's the question, why should you even do it? Or should it even perform nicely on a GPU? So there's first of all, for GPU, you want single instruction and multiple data. Here, the Bayesian calibration is somewhat nice because actually the workhorse is just the matrix, and especially from CUDA side, there's a lot of stuff already implemented on linear algebra. So from that part, it looks good. And the rest of the operations are also just matrix operations, so that should be helpful. And second of all, you want a high arithmetic intensity. That means you don't want to move data around a lot, especially not between host and device. And here, the thing we can profit from our problem setting, that we have a lot of simulation data that doesn't change, that's fixed from the beginning, and only a small amount of parameters that we're actually inferring that are changing between the sampling steps. So we only move the big bunch of the data once to the device and then keep the data, only shuffle around the inferred and sampled parameters. And the return probability, but which are also just a few numbers. So as you can see, we tried it out. It worked. We got a nice speed up, especially if compared to the CPU. For the CPU, you see that it grows quite fast. For the GPU, you see that for the problem sizes we tried, you have quite a big overhead. So for the small problems, it didn't help. But from a data set size, for the simulation data set from about 100, we start seeing better performance on the GPU that doesn't grow as fast as it does for the CPU. So that's very nice. It takes over about 100. And we get a similar speed up to the other trick that we used before, just on the CPU. But there's a big caveat in what we had to do to achieve it, which is the problem at the moment is the big problem. So to adapt it for the GPU, we first of all had to rewrite some functions with the dispatch system to actually work with CUDA arrays. The problem is that the distance.gl package on which the kernel functions.gl package is kind of founded on or based on uses a lot of scalar indexing loops, which basically you have to rewrite. So you know the kernel that you use to rewrite that one, and that's fine, okay. Then there's a small number of other functions, like calculating the log determinant and a kappa function, which is also from the distance.jl, which you rewrite. Those are relatively small functions. That's fine. But then, because you would like to use the nice Hamiltonian samplers that are available in Turing, you find, oh no, basically automatic differentiation is a big problem. We tried it with Mooncake and Zygote. In the end, we got it to run by basically rewriting for our concrete one version case a lot of RR rules, so that we get around the CUDA functions, especially around a lot of try-catch in the CUDA functions, which are a problem, especially for Mooncake. But we had to rewrite even a special RR rule for the log PDF function. So the problem is that this leads to a very, very highly customized code for one concrete problem. It was nice to find the performance improvement that we could achieve, but on the other hand, we had the problem that we don't think this problem is really, really maintainable for us in the long run, because we still want to keep the flexibility that was the whole point of starting with the nice Turing models. So we are still trying around, maybe finding something in the abstract kernels JL to get around some of the problems we had with the automatic differentiation, but yeah, that's the current state. Again, a small summary. So basically, the performance speed up on the GPU is promising, but it's hard to maintain this code. Thank you very much for your attention, and are there any questions?
Thanks, Sebastian. So we are open for questions indeed. Here and then here.
Thank you for the talk. Is it feasible to just rewrite distances and the kernel functions, the JL packages, to get rid of the scalar indexing?
So probably it is feasible, because in the end, those are not so many functions. It's probably the distances packages looks like it's written that way on purpose. So the idea is they basically define an abstract metric which they can pass around. Obviously, if you say, okay, we just use Euler metric, very simple stuff, rewriting that part is feasible. But you will, again, lose the flexibility of being allowed to use some kind of differential geometry metric that somebody likes to have for some reason. Yeah.
Over here. No, you need the microphone for the streaming.
Okay, thank you for the presentation. I have a question on how do you define your kernel function? And
so in our case, we use the Martin 3.2 kernel, because that's just a good trade-off for us between the assumed smoothness of our functions while allowing for some unsmoothness due to the measurement errors and stuff like that. But it's very, very easy to switch around to go to other Martin kernels, of course, but also use squared exponentials. But obviously, those are the only ones we tried on GPU. Yeah.
Okay. Yep. Thank you.
Welcome. Okay, we have time for a last quick question. Yeah, another one from Robert.
Hopefully quick. I was wondering, do you assume that the simulation is perfectly accurate? Or can you take into account the fact that maybe the simulation are off when you do the calibration?
So I didn't go into that part, but we use the Kennedy-O'Hagan calibration model, where you explicitly have a separate term that tries to capture inaccuracies in the simulation. But it gets subsumed in the kernel function because it's just one big GP. But yes, we have that into account, and yes, yeah.
Great. Okay. It's 1 o'clock. It's lunchtime. Let's thank all the speakers again in this session. Yeah, and I wish you an enjoyable lunch, and things restart at 2:30.
I can, because All right. Good afternoon, everyone. Welcome to the 2026 edition of the Julia Molsim mini symposium. My name is Ray. I will be chairing this mini symposium this afternoon. First of all, a quick announcement that unfortunately we have 2 talks got canceled because of family emergency and medical conditions. But luckily, we have added a discussion panel session to fill the gap. And what's even better is that some folks from ASML who actually have material science background want to join and will be on the panel, then also want to interact with the community with presenting their material science problem. And then a task for you, for the audience, is you should think about whether you have the tools or ideas to solve their problems. That's a way to connect us as researchers and scientists to potential very useful industry applications. So that discussion panel will take place at 4:45 p.m. to 5:15. Without further ado, let's start with the first long talk of the session by Daniel Katz and Charlotte Rickert from the Max Planck Institute for Solid State Physics in Stuttgart. Daniel, the floor is yours.
Thank you. So this talk will be about our package LM-Coil, which is a Julia package, of course, for treating electron correlation in molecules and solids. And the molecules and solids are here. So what we want is to describe electronic structure of these molecules, calculate the stability of the molecules, how they interact with each other, or maybe also treat some local defects in periodic systems or periodic systems themselves. And the good part of it is that we just have to solve one equation, the Schrödinger equation, which is also not very long. And if we write it in the one particle basis, it's also the Hamilton operator doesn't look very scary. You have just 3 terms: scalar, matrix, and ranked 4 tensor. And usually this Hamilton operator is also Hermitian and real, but not always. So we also sometimes want to treat some non-real or non-Hermitian Hamiltonians. And one can, if one works in this one particle base set, one can also expand the wave function in terms of Slater determinants, which just represent how we distribute electrons among orbitals. And then one has a matrix eigenvalue equation, which one can solve, and this corresponds to the exact diagonalization of the Schrödinger equation in the given basis, but it's of course also very expensive. So with this we can really treat only very small systems. And and unless you have some quantum computer lying around, we have to come up with some approximations. And one approximation is, for example, we restrict which determinants we treat. This is like we select only the most important determinants, and this is the idea behind selected CI, which of course results in a sparse coefficients and sparse storage of Hamilton elements, so we have to deal with those. We need some tight loops to be fast and so on. So this is one of the requirements. Another idea what one can do is to change the ansatz for the wave function and use with this work with this product ansatz where we have some amplitudes. Do you see? Oops. Can we see? Yes. Amplitudes and these amplitudes they are just multi-dimensional arrays or tensors, and they can be quite huge if we go to larger systems. But the good thing is that we really need just tensor contractions most of the time. So as long as we can write the tensor contractions easily, then we can easily implement those methods. And the methods, this couple cluster methods, also very accurate. Now to the size of the systems we want to treat is like this benzene dimer, which I showed on the first slide. And if we want to treat it in the reasonably large basis, then it's around 800 orbitals what we need. And this means that our rank 4 tensor in the Hamiltonian is around 3 terabyte, which can be reduced if you use permutational symmetry of the tensor, but this is the amount around 1 terabyte what one needs for this size of the system. And the amplitudes which describe the correlation, well, for the double amplitudes, which are like the most important ones, we just need like around 4 gigabyte, but if we go to the next level, the triple amplitudes, then it's already around 100 terabyte, and of course we can't really treat it, so Charlotte will present you with our ansatz how we can extend this kind of methods to larger systems. Now, why do we want to implement this, or why did we implement this in Julia? And well, basically the most important part is that there was already a tensor operations package available, which allows to really quickly implement tensor contractions. So, implementation of like couple cluster was 1 or 2 days without AI. So that was very nice. And yes, if you know the tensor contraction, the package, it's really, you write your expression, basically it's as easy and as readable as just the equation itself. So that was really a pleasure. Then there are these usual suspects like multidimensional arrays out of the box, efficient loops, and then multiple dispatch where we can, and also just-in-time compilation, which allows us to have real and complex integrals and non-Hermitian integrals very efficiently. And yes, also other stuff. What I also like is that the input file can be really the code itself, so we can really access any internal functions or whatever we want from our package. But at the same time, it doesn't really have to look like a code. So if you use macros, it really can look like a like an old style input where you just really write what you really want to do. Like you define your geometry basis and then just the methods which you want to run. And this is still the Julia code. So it's very nice also, for non-Julia experts to use. So then there are also some problems which we encountered. And the main one is with the garbage collection, with memory management, because as you know, we have these large tensors and we have to loop, slice them, and we have some intermediates in the loops, large intermediates, so it dies very quickly. And then instead, we introduced a different package for manual memory management called buffers. And if I have time, I will just briefly introduce it afterwards. Yeah, there are also some other issues, but okay, I will go to the next slide. So this is the package what we have, LM coil, which is mainly for describing electron correlation methods, and it's registered. You can easily install it. It's on GitHub also, and we have a web page, LM coil, which you can also access for the documentation. And yes, the input, it's the same input, but now in the functions, just to show that we don't have really this global variables. So your input can be actually be part of the program and be part in the function. Yes, how do we specify the system? It's the usual way, so if we specify the geometry of the molecule, where the atoms are located, and the usual acronyms for the bases like AVTZ, VDZ, whatever. You can also specify the bases more, accurately using exponents and contraction coefficients, but this is more for experts. Then the other option is to have to provide the integrals directly using the FCI dump format, and because we use this very easy to use input format, we had to reserve this variable name. So geometry basis in the FCI dump, if you write it there, then the geometry and the basis, then the macro will look for these variables and take the system out of it. There is also an option now to get integrals from WASP, but yeah, I won't talk about this now. And yes, what the macros do is to put the EC information, put this in the variable called EC, and then in this EC information there is like a Scratch directory, the system itself, and so on. And yeah, I think that's it. I just wanted to show you, there are many methods implemented. We have this Hartree fork, which defines the reference coupled cluster, and then one can define which coupled cluster method one wants to run. Then there is selected CI and many more. And yeah, I will skip the rest. And then, yeah, there is this buffers, as I said. We have also some other packages. Some of them are registered, like buffers, some are not yet. But yeah, I will just give the floor to Charlotte to talk about some specific methods.
Hello. Yeah. Thank you very much, Daniel, for this very nice introduction to LM-Coil. I will start again with a little bit of chemistry motivation. So usually as chemists, people are very interested in reactions, right? So it can be anything, some A plus B will react to some C plus D, whatever. And maybe you know it's still from school. You have always some reaction scheme where you have the reagents, some transition step, and some products. And of course, everywhere energies. So that's why we are super interested in them as chemists. As Daniel already said, for this we have to solve the Schrödinger equation, but it's not as simple, right? So one can say that the theoretical prediction of energies is desirable, but it's a highly complex problem. So theoretical chemists, for everyone who's maybe not heard of it, call the most difficult part correlation energy. So E correlation, which is basically the exact energy. So exact in a sense, okay, time independent, Born-Oppenheimer approximate the Schrödinger equation. Which then, so this is called Hartree-Fock, the reference method, which was already mentioned. So this is very easy to obtain, relatively easy. So we are very interested in those correlation energy to fill this gap to the exact energy. Okay, nice. So again, for everyone who's maybe not a theoretical chemist, we always introduce a basis set, which is some sort of spanning our basis. This is like some Gaussian basis functions usually. And of course, the exactness increases, the better the basis is getting, and the better also the method is getting. There's one solution, full CI, which is actually exactly solving the Schrödinger equation. But the problem with this is that it has really nasty factorial scaling, so it's just way too expensive. So that's why usually, or we try to use coupled cluster. It's the gold standard of quantum chemistry, CCSC parenthesis T, parenthesis T, some perturbative approximation to excitations. So now I will focus in my part on the question how to call your head around tensor decomposed distinguishable cluster. So we will split the talk in 3 parts. What is distinguishable cluster? Then what is tensor decomposition, or how can we use it? And then, well, of course, we will have some part on LM-Coil again. Okay, so think again of the Schrödinger equation. You have there some eigenfunction of the Hamiltonian, which is, of course, the wave function method. And here you see the ansatz for the coupled cluster wave function, short CC. And you have the reference state, can be anything. And you have some exponential to the power t. This is some operator. Don't be afraid if you don't know quantum mechanics. Basically, it's just some sort of subsequent electron excitation operator, which is defined as some coefficients. So it's just coefficients which we need to solve here, called t, or amplitudes. And you have here creation and annihilation operators, which are sort of spanning your basis. So those are acting on the reference function, and you just span your basis in some sense. If you see some exponentiated operator, you probably think of Taylor expansion, and that's one of the strengths of coupled cluster. It can be Taylor expanded, which leads to some very nice properties for coupled cluster. I will not go into detail, but if you maybe heard of size consistency or size extensivity, it will ring a bell. So depending on where you truncate now your operator, so after singles and doubles excitations or triples, you call it CC singles doubles or CC singles doubles triples. So it's some sort of hierarchy, and if we would, put this to like very large or high excitation level, then we again obtain the perfect solution. So the energy expression is very easily obtained by projecting the reference from the left, and then we have some residual equations. That's actually where the numerical mathematics kicks in, because to solve our Schrödinger equation, we need to sort of make them zero by solving for our coefficients called t, and if everything is at least close enough to zero, then we know it's converged. And of course, those methods are implemented in LM-COI, right? Otherwise, why would I talk about them? And then now let's talk about equation of motion couple cluster theory. Don't be confused. It has nothing to do with classical mechanics, but rather with electronic excitation energies. Yeah, I'm sorry for that very easy picture. But so you have some photon which is shooting at some ground state of the molecule, and then you have some electronic excitation, right? And this is of course important for solar cells or also photochemistry or photophysics and so on. So you want to use it. This is a little bit more advanced picture. So of course we're talking about vertical excitation energies here. And now let's look again at some wave function, which we again need, but now for the excited states. And now we come back to our coupled cluster, which is here, and we have again some excitation operator. This time it is linear, so not exponential. And it's again just split up, and we have some coefficients called R, which we have to solve on top of the coefficients we already have for coupled cluster, which of course makes the problem a bit more complex, but fine. So then after some mathematics, which I will not discuss here in detail, one comes to some similarity transformed Hamiltonian, some linear operator, and of course it reminds you of an eigenvalue equation because it is also one. So this is clearly an eigenvalue equation, and you can just solve it with Davidson or whatever. So equation of motion coupled cluster methods you can also find in LM-COI. And now let's talk about some challenges of coupled cluster theory, right? So it's really great, but not everything is great. So for example, it has very steep scaling. So if your basis is large, it's scaling n to the 7th. This is really like huge and unaffordable for larger systems usually. It's failing for methods because of the perturbative nature of the triples. It's breaking early for strongly correlated systems. Strongly correlated here means, for who doesn't know, for example, for transition metals, it's failing if you split some bonds up, if they're having sort of multiple bonds at once. And also there's some dispute how accurate it is for big systems, but it's some sort of not so important for the moment. If you then go to iterative triples, so this full T we showed, we see that some of the challenges get removed, but it's even, more expensive. So this is really like almost unapplicable to anything like bigger. And also the performance, even though we have increased cost, is not so much better. How about excited states? There we also have problems, of course. So it's having some problems like CCSD for the ground state. The error can be large for some cases. And it's computationally at least not inexpensive, so n to the 6 scaling, which is also really large. Okay, so what can we do then? So now let's talk about the distinguishable cluster approximation, and you have to know that in LM-COI we have used distinguishable cluster a lot because it's a really promising approach and it's not really there too much in other program packages. Okay, let's think together. So we have a molecule. I know it's again an awful picture, but it's a sort of a triple bonded nitrogen-nitrogen molecule, and let's just split it. Okay, so it's split, and of course it's important for chemistry, right, to split up some molecules for reactions, but truncated coupled cluster, so CCSD, for example, CCSDT, is failing for those things. So then it was suggested that this failure maybe comes from specific terms in those residual equations, so those which should be equal to 0, and so in case the orbitals are not localizable on each atom, that's why distinguishable cluster was introduced to CCSD. Here again our residuals. Those are some Feynman diagrams in those equations. Doesn't matter that much. But we cross out the problematic terms, but still our wave function should be size extensive, particle Hall symmetric, and most importantly, exact for 2 electron systems. So distinguishable cluster, DCSD, if you introduce here some other factors, is solving the Schrödinger equation for 2 electron systems perfectly. So as good as also CCSD. Okay, so DCSD is improving everything. So reaction energies, ionization potentials, interaction energy, spectroscopic constants, like literally everything. And to bring the story to an end, it's also introducing, so this is like N2 dissociation. The really expensive but perfect reference is MRCI plus Q here in blue. CCSD you see is failing, it's just breaking down, but all versions of DCSD are qualitatively describing this, and this is really astonishing for theoretical chemists because it's a single reference method and it's still working really well. For excited states, we also look here. You see CC3 is a reference, and for the excited states, so we see CCSD, so this is the perfect line. CCSD is for almost all states further away, which is also great. And just think, so we removed some terms, so it's not more, but rather less expensive and still better. Okay, now we can also introduce this. If DCSD is not exact enough, this still triples excitation. So we keep some constraints. Now we want to have it exact for 3 electron subsystems. Yeah, so triplets really have a lot of terms, like 200 or something, so here just some contractions. So we cross some out, rescale again to fulfill our constraints here. Perfect. Let's look at the accuracy. You see DC-CCSD is outperforming parenthesis T, and also CCSD full T. Also for intermolecular interactions, so what chemists are really interested in, also let's say for proteins, it's really working well. But unfortunately, it's still computationally very demanding. So what can we do then? For example, so the scaling is here, for example, n to 6, n to the 8, n to 6. So what to do then? So let's talk briefly about singular value composition, which you probably already heard of. So you have a matrix A, M cross N, and it's represented using singular value composition as a product of 2 square matrices as well as 1 diagonal. And here those contain so-called singular vectors, and those are so-called singular values. And now we apply it, so in LMCOI we have implementations for all methods. I will focus now only on triples because it's the highest scaling one. And you see again here our coefficients. Yeah, so remember, if we have them, then we solve the Schrödinger equation exactly. So we can do this, and we can neglect those singular vectors which correspond to smaller singular values, because the smaller the singular value, the less important those singular vectors are for the representation of the triples amplitudes. And now we can factorize this as a product of a 6-index tensor in the form of a symmetric sort of 4-tensor product. And we will call from now on the threshold of neglection epsilon T3. Okay, so now how is it benefiting the distinguishable cluster algorithm? So let's look at the algorithm. So we guess the amplitudes, we calculate the residuals, then we update our amplitudes, and then we do this iteratively until convergence. Okay, so we see that we have all of the quantities in the SVD basis, so we get rid of those 6 index quantities to store. So we have already some sort of memory benefit. But additionally, we introduce flexibility for tensor contractions. So this is some term contributing to the residuals. It's just some Feynman diagram, and this is very famous density fitting. You can split up some integrals. This can downscale some things, but this is the bottleneck of our calculation, so it's not helping. It's n to the 8th. Due to tensor decomposition, we can split up those diagrams even further and can rearrange them, which now, if we look at the bottleneck, gives us a very lengthy expression. But now this can be reformulated, so the scaling is reduced to n to the 5th, so 3 orders of magnitude smaller than what we had before, which is really great. And if you do it for all terms, like 200 or something, then you can see that the scaling can be reduced to n to the 6th overall. And also the decomposition algorithm scales at n to the 6th at most too, so it was not shown here because it's too complex to really describe it. But now also you can apply it for the different distinguishable cluster methods, and it's always reducing the scaling. So here I just showed that the approximation, the tighter you make the threshold, the closer it gets to DC-CCSDT. This is some other quantum chemical method which is even more accurate. It's also performing well. In that case, there are some tricks how to make quicker conversions. And yeah, this is by looking at, again, the residuals, defining some different, sort of identifying the most important terms by perturbative orders. And with this, we converge even quicker, which is great. So now we can go to also bigger basis sets. We have similar trends. Now we also show that size extensivity is kept. and that the SVD basis size is growing linearly. So this is some carbon chain, it's getting longer and longer. And because this is linearly scaling, we can eventually claim actual n⁶ scaling. Some highlight application. So a lot of chemists like to benchmark stuff on benzene. And for triple zeta, so we look here at our CCSD implementation, and even though we include full iterative triples, we just have 4 times more timing consumption, which is really great. Then the bigger the basis, the more saved. Here's some molecular dissociation. This just shows that the SVD approximation doesn't harm the benefit of the single triple cluster. And here also for intermolecular interaction, it's also working great. Okay, so now we come back to LM coil eventually. And now I give a hands-on example to show that it's really easy to use also for non-experts. Okay, so let's type Julia. Okay, great. Now, of course, we have to give a molecule. Now we give water. Okay, first line, water. Now we give a basis. Okay, double zeta, second line. And then already in the third line, I forgot using LM coil. Perfect. Okay. Okay, sorry. Okay, so first we have to use, of course, LM coil. Then we again specify geometry and basis. And then the actual third line is the reference calculation density Hartwig Fock. So it's extremely easy to use. And now we can immediately calculate the gold standard. CCSD parenthesis T is already done. Now we can go to some singular value composed methods, as well as some excited state methods. So it's very easy. It's just CC and then the respective method. Okay, so we have some 1 excitation energy, really great. And if this is still too complicated for some users, we have also, as an alternative, some visualization program called JL-Mol. So you can theoretically go to any molecule. We also have, I don't know, caffeine, ethanol, whatever. You can 2D edit something, and then it will be force field optimized in 3D. We have also some connection to XTB. Maybe some people know this from Stefan Grimme. It's better than force fields. And then if you click on the LM core logo, if you're happy with your geometry, you can select your basis set. You can select your methods. So for example, Hartwig Fock, okay. Let's select again some singular value decomposition. And then you have a lot of options to choose from. Let's say we want to tighten our threshold. So this epsilon T3 I showed. Then you can just, for example, add a 0. Okay, great. And then you can see here, it's automatically generated your input. You can just copy to clipboard and immediately start it at your server of choice. So it's extremely easy, which is especially important for chemists, as they say, experimental chemists who are not so much into programming or anything. And also a benefit is that everything, as Daniel already said, can be accessed from the input file. So it's really great. It's super easy to use, and you can also extend easily your own methods. So if you have ideas, you can always just use LM coil. So now we saw electron correlation methods, a lot of tensor decomposition, a lot of distinguishable cluster, and we are open source. So please just use our package if you want. If you want, you can scan the QR code. You can also take some stickers. And yeah, so again, we have such a great variety of innovative quantum chemical methods. We can connect easy to other quantum chemical software. The development is ongoing, and we're very happy to find contributors, so we search for you. Also as users, of course, so just contact us. We saw also strengths of distinguishable cluster methods for grounded excited states, and tensor decomposition can be used to lower scaling of quantum chemical methods significantly. So we want to acknowledge MPI, Humboldt University, DFG, and Studienverfügung Deutsch und Volker, so thank you very much. And thank you very much for your attention, and thanks again to Daniel. And now, that was it. Thank you.
Talk. Let's have 1 or 2 quick questions. I know for a fact Daniel and Charlotte will have a poster session this afternoon. Any quick questions?
Yeah, hi, thanks for the talk. I mean, it's quite impressive how it's improved since the last version of the talk I saw, I don't know, maybe a year and a half ago. I'm a little bit interested on sort of the background of all of this. Like you basically showed a very nice quantum chemistry interface, but of course as people from the MULSIM community working with atom structures and so on, I was wondering to what extent you are integrating with that, and what would be the possibility to integrate in case that's not yet done. If there's like data structures, for example, one can pass around with the data from the computation of the respective coupled cluster methods, scriptability, and so on and so forth. Maybe you can say a few words about that.
Should I go to the Trexio slides?
So, I mean, we have an extension to Atom Space, so one can probably read. I think one can read and write Atom Space from and to the code. So we have also this TRX-IO interface, which is like a general way to store wave function information like orbitals, also integrals, whatever. This is also, can be used with many quantum chemistry codes and probably not so difficult to implement also in other codes. So that's sort of, yeah.
Yeah, let's thank Daniel and Charlotte again. Please find them at the poster session. Laser-driven hydrogen evolution with NQCD dynamics.jl, and very interestingly, how Julia and Python can live in harmony. Please, floor is yours.
Hopefully harmony. We'll see. So thanks for the introduction. I'm going to talk to you both about a bit of my particular PhD research and also in general about something that my whole research group has been working on for a while now, which is this package called nqcdynamics.jl. First of all, I need to temper your expectations a bit because laser-driven always sounds very cool, so you might be imagining something like this. Unfortunately, all of the lasers featured in this talk look a little bit more boring and very theoretical. So yeah, just a word of warning to start off with. But first of all, I'm very happy that I'm not the only person to have brought the very basic chemical reaction picture to this symposium for the benefit of any non-chemists in the audience. Well, we chemistry people are very interested in looking at reactions, and any kind of process that we might want to see happen can usually be boiled down to this sort of energy hill that we have to move over in one or the other direction. And typically the way we do this is using catalysts to change the height of this barrier and by heating everything up so that by pushing everything around, we increase the chance of moving over this barrier with enough energy. But of course, just heating everything up is a little bit inefficient because you're having to provide energy into every single degree of freedom in your system rather than just the few degrees of freedom that might matter for a chemical reaction. So how does light play into that? Well, you have access to electronically excited states, and so what looked like a barrier in the ground state might look very different in an excited state, so we can bypass some of the barrier, ideally. And there's a lot of factors that affect how this works. And even if you find a material that happens to be very good at promoting these sort of light-driven reactions, you then run into questions of size and shape and selectivity, because of course there might be multiple different processes happening and competing against each other. And so really what we'd like to do is we'd like to understand computationally how we can make specific processes happen under the influence of light, and just as some examples where this might be useful, you know, several different large-scale processes where any kind of better understanding of how we can increase energy efficiency, that would of course be very nice. So, okay, let's try and tackle this sort of problem in Julia. How do we do that? Well, if we want to look at mechanisms, so how does a particular reaction happen, then we need to do molecular dynamics. And okay, there are molecular dynamics solutions in Julia. There are different ways of getting energies and forces to propagate molecular dynamics. You could use your favorite machine learning solution, but unfortunately that doesn't really get us all the way there yet. And there are usually, well, there are two sort of distinct problems. The first one being, we need to describe in some way how the interaction with light affects our molecular dynamics. And the other problem is, not all of the machine learning models that we might want to use are necessarily written in Julia. Unfortunately, we're still a bit of a niche language. So let's focus on the first part first and talk about light-driven dynamics. So let's start from sort of classical dynamics first. Usually, you know, in the previous talk, we've heard all about excited states, but if we're doing molecular dynamics, we usually just focus on one electronic state, and we usually assume that because our electrons are so much smaller than and weigh so much less than the nuclei, we can decouple their dynamics, and this is what's known as this Born-Oppenheimer approximation. But once you start including excited states, this approximation starts breaking down, and I'm incredibly proud of this animation right here. And so instead you run into a picture where suddenly things become very time-dependent and very coupled to each other, and that then means that the computational scaling increases dramatically, which is all pretty horrible to solve, particularly if you want to look at things happening over longer timescales. And since we usually want to look at processes out of equilibrium, the way we simulate that is we take our system, we poke it out of equilibrium, and then see how it recovers, to understand how it recovers. Now, that might happen in different ways between different simulations, and so we need to run hundreds, thousands, potentially hundreds of thousands of simulations and sample statistical properties. And that then becomes even more of a pain to do if you've got this sort of computational scaling. And a way of bypassing some of this is using these mixed quantum classical dynamics methods. And so the idea here is you go back to the safety of the Born-Oppenheimer approximation and say our nuclei are moving for the most part classically, but then we add on some sort of correction that might include some quantum mechanics that accounts for the coupling between electronic and nuclear degrees of freedom. And there are many different methods you can use for that. I'd say they sort of boil down generally into two different categories, where one is slightly more explicit, where you're looking at different electronic states and deciding when to switch between them. Those are these surface hopping methods, or other methods where you take one state and add a perturbation to it. Ehrenfest dynamics is an example for that. So, okay, there's a bunch of different methods we can choose. Some of them might be good, some of them might be bad for a particular process or a particular system that we're interested in. So we're probably going to need to compare a few methods to each other. Maybe also benchmark them to see how efficient they are. And this is where this package comes in, or rather this set of packages with nqcdynamics.jl, where the idea is to provide a framework for running simulations with different mixed quantum classical dynamics methods, developing new methods on one hand, but then also being able to scale up the whole workflow to run hundreds of thousands of simulations once you're happy with your choice of method. And this originally started as a former PhD colleague's side project about 8 years ago, and we're now, I'd say, sort of 4 or 5 people more or less actively developing on top of that. It's all a bit modular, so different components are split into different packages, which hopefully makes it easier for people to contribute certain things. So, for example, we have a collection of models that are typically, like potential models that are typically used for these benchmarking studies in nqcmodels.jl. There's something to handle the generation of initial conditions in nqc distributions, and so on. And all of this is quite nicely integrated into various different parts of the Julia ecosystem. So molecular dynamics and mixed quantum classical methods in general are really just differential equations. And so we can make use of the differential equations.jl library with all of its useful functions and features. And we've connected up a bunch of interfaces to different things to be able to connect up to quantum chemistry codes, machine learning models. We speak atoms-based and atoms calculators. So yeah, that's kind of the package pitch. And now let's talk about mixed quantum classical dynamics in a bit more detail. And for this, I thought I'd just show you a very simple example. So this is sort of a typical testing model with a one-dimensional system, and we're going to use a method called independent electron surface hopping. The way this works is you calculate different electronic states, and the nuclear dynamics change by basically switching between these different states, and you have some sort of likelihood for switching between these different states depending on what happens to the electrons. And so in the graphic that I'm going to show you in a minute, you'll see some electrons in different energy states on the right-hand side, and I'm going to throw a particle at the surface, which will eventually come. There we go. And as it kind of goes up this hill and bounces back, you can see some of the electrons have moved around. So there was some exchange of energy between nuclear motion and electronic excitation. And again, this is just a very simple example. There's a bunch of similar methods of this type where usually what changes is the mechanism for switching between different electronic states. And there's a whole tutorial for setting all this up. If you're interested, I'm also going to show a QR code to download the slides at the end. So you don't have to worry if you miss any of the QR codes. But OK, that's one big class of methods. The other big class of methods you can use are these mean field methods. Here you pick one electronic state, usually the electronic ground state, and add some sort of mean interaction with all the other electronic states in the system to it. And so instead of hopping between different states, as you can see in the picture on the left-hand side, this is more like it is on the right-hand side, where one state is kind of smeared out a bit. And one method I'm going to focus on in particular is this molecular dynamics with electronic friction. So just as an example, I'm showing you the equation of motion here, which starts off very classically with this first PES term, and then you have a friction and thermal fluctuations term, which are sort of the non-classical contributions in this case. And This method in particular is good for the kind of system that I'm describing, which is hydrogen evolution from metal surfaces. And because a metal has very many electronic states, we really don't want to have to do surface hopping to try and start counting thousands of electrons into potentially thousands of states. So something mean field is a lot nicer for this sort of thing. Okay, that's a very quick rundown of mixed quantum classical dynamics. Now, for my particular case of hydrogen evolution from a copper surface, there's a bunch of different effects that need to be described. And unfortunately, a lot of them take place across different timescales. So, interactions between the laser pulse and the metal surface happen very quickly, but then relaxation and energy dissipation takes a lot longer. But okay, so if we kind of go through our shopping list of what we need to be able to describe, we've talked about one part now, which is this electron-nuclear coupling. We've talked about the fact that we need to statistically sample. And now the final part is we need some way of describing how light interacts with our metal in the first place. And there are many different ways you can do that. And this is the point where I plug Henry's talk, who's going to be talking later, who has spent a lot of time on trying to bridge sort of the gap between timescales, because generally you have the option of being very accurate in what's happening between sort of what happens, how light excites individual electrons, but we can only really do that for short timescales, not as long as we want to do dynamics for. Or we can go the other way, which is a very implicit empirical model with something like a two-temperature model, where we're not really thinking about light, but we're just kind of dumping energy into a system and calling it light. So I'm not going to say too much more about light-matter interactions. So let's just assume we've found our way of doing this. So now we have a method, and now we want to make it fast. This is where a lot of people now do machine learning. And so, you take a bunch of different structures from, say, DFT calculations, train machine learning potentials on them. You can go through these active learning loops where you take your first generation model, run some dynamics with it, check back against the DFT that provides your reference data, and find the points where you're making mistakes. Learn from those mistakes by adding that data into the training for future models. And by going through this loop a few times, you've now got a model that works a lot better and hopefully is also quite a bit faster than doing the actual DFT calculations. And so here's some benchmarking that a previous colleague of mine did on a bunch of different machine learning frameworks. And there's quite a lot of stuff to see in this particular picture. Perhaps most notably, ACE potentials was lovely and fast, but unfortunately not as accurate as some of the other methods. In the end, we kind of picked MACE, which is this one particular machine learning framework written in Python, out of all of these methods here. And you can obviously make that work by using something like Python call to integrate the Python-based machine learning code into your workflow. And I was, of course, wondering, is there any way I can make this faster? Because after all, people say that Python is slow. Whether that's true or not, I think is debatable. But surely there's got to be some way of making this faster, and I tried. I really tried. So the idea is basically the machine learning inference code runs in Python because that would be too annoying to port to Julia and maintain every time the Python version makes changes. So let's try and be minimally invasive into the Python side, and we need some way of going from from a structure on the Julia side to having energies and forces on the Julia side. You can use Python call for that. That's all very nice. You can even use something like dlpack.jl to share memory between Julia and Python and transport references to arrays back and forth, which is nice because that means less copying around of things. More recently, there are good and fast Julia-based neighbor lists as well. And while I wish I could say that all of this stuff that I wrote makes things a lot faster, it's maybe a few % at best. So unfortunately, not much benefit there, but I tried. Okay, so that's one part of the story, which is a lot of people, when doing machine learning, focus on energies and forces, but of course that's only part of the whole story if you're doing mixed quantum classical dynamics, because we're only really accelerating this first term. And this sort of thing applies, whenever you have an additional quantity that you have to calculate using quantum chemistry methods, perhaps you can machine learn it. In this case, luckily enough, we were even able to do all of this in Julia, and so we have machine learning models using ace potentials and a derivative of it called ace friction to calculate these red lambda parameters here, which describe how strong this electron-nuclear coupling correction is. Okay. And so now the final thing to do is to run it hundreds of thousands of times. And so you'd think, because everyone always says machine learning is great on GPUs, that I would want to run everything on GPUs. Interestingly, that wasn't the case. So I tried a bunch of different things, and in general, I always reached the point where just putting everything embarrassingly parallel onto CPU cores, one CPU per simulation, gave me a much higher throughput of simulated time than anything else on GPUs. So I tried different things. I tried having one copy of the machine learning model sitting on a GPU and dishing out information to a bunch of other processors. That slowed things down a lot more than more recently on GPUs with much more VRAM. You can just have many, many copies of the same model running on one GPU. That also doesn't really speed things up very much in my case. But okay, going back to the shopping list of things we needed, we now kind of have a solution for everything. And so let's put together all those pieces and have a look at a lovely animation. So here you can see my copper surface with some hydrogen atoms on top in white, and they're going to start moving around a bit now. The laser, which we're not going to see, hits the surface at a time of 0, and so you can hopefully start seeing the hydrogen atoms moving around a bit more until eventually they collide and leave the surface, which I think is happening now. Yeah, there we go. And so again, if you want to see the practical side of how all of this is done in the code and all of the machine learning stuff is connected up, I've written a tutorial for that. One of these simulations takes anywhere from about 1 to 3 hours. Now, because it's not guaranteed that the desorption happens at a particular time, some simulations might end early while other simulations don't, and that also makes things a lot more difficult when you talk about parallelization, and so I'm happy to take any suggestions that you might have. But yeah, so we've done this once, now let's do it 350,000 times and hope we didn't make any mistakes, because that would waste a lot of computing time. And we can look at some final statistics. So this is more just an example and not a particular scientific point that I'm trying to make. what I can say here is that each of these data points that you're seeing is the result of about 20,000 simulations that you saw before. And the two different curves that I'm showing you here are just different ways of calculating electron-nuclear coupling within this electronic friction idea. And yeah, in this case, unfortunately, I don't really have an experimental curve to draw in there, which is unfortunate, but you know, work in progress. And that kind of already brings me to the end. So hopefully I've provided a few examples how NQC dynamics might be useful for you, if that's the sort of thing that you do. I've hopefully showed you some of the perils of trying to combine Julia and Python together in a performant way. I'm, in general, very happy with how things are constantly improving in sort of the Julia Molsim ecosystem, because there's a lot more interesting stuff to play around with and try and integrate than there was when I started with this whole thing. And just in general, if there was anything interesting in my presentation that you'd like to ask me questions about beyond the Q&A now, I am going to be at our NQC Dynamics poster later, and with that, I'd like to thank you all for listening, and I'm happy to take any questions.
Thank you very much for the very interesting talk. We have some time for some questions. Anyone?
Hello, so your model with friction looks a lot like a Langevin equation.
Yes.
So could you tell about it's deterministic or?
So it is stochastic dynamics. Still, it is basically a Langevin equation, but with a more complicated friction coefficient. So generally in Langevin, you'd have a single friction coefficient that affects all degrees of freedom equally, whereas in MDEF, you have a friction matrix where different degrees of freedom experience different friction.
But you have no memory, so it's a Markovian.
Yes.
Okay. Thank you.
Thanks very much. So if I understand correctly, currently for your electronic structure, you're using these learned potentials.
Correct,
and I was wondering if, for example, for a simple system, I would like to go to the trouble to use an ab initio one, how much work it would be to plug in another electronic potential electronic surface from another code.
So that should be reasonably simple to do. So I don't think we've actually done that yet. So right now, what we'd be able to do would be to take in, single electronic states from a DFT code. Somebody would have to build effectively a model template that extracts all of the info that you need. But the framework for it is already there because we have the models that can handle n different states, if that kind of makes sense.
Any more questions? I have a question about your attempts on accelerating the GPU part. I think the only way you can gain a lot of speed up is by changing the data structure, which is not something you can easily do if you use the Python maze backend. And then what you're trying was basically changing the way of scheduling jobs and distribution on the GPU nodes. Is there any plan to have a more performant backend, like say a Julia version of Maze?
Well, I think that would be very nice to have. I'm kind of worried to throw that idea at an LLM and have it come up with something that probably works initially, but then will be very difficult to maintain longer term. I think that's the difficulty if you were to, say, take something that's already established on the Python side and just straight translate an interface for it. We are looking at different ways of using ACE potentials instead of MACE. They seem to require a bit more training data, but it does also seem possible to use ACE potentials, and they would run quite a bit faster still. So I think it's probably better to capitalize off of what we already have in the ecosystem before trying to just straight translate.
Yeah, that makes sense. All right, let's thank the speaker again. Let's welcome Noé Blaser from EPFL telling us about computing transport coefficients using Molly.jl. Floor is yours.
So thank you very much. So I'm Noé Blaser. I'm currently a postdoc in the Mathematics for Materials Modeling group at EPFL. But here I'll talk about some work I did at the beginning of my PhD with Gabriel Stolz at École des Ponts. And the goal is to compute transport coefficients using Molly. So first I'll talk a bit about transport coefficients. So the goal is to predict macroscopic transport laws from microscopic, so molecular dynamics simulations. And I'll talk a bit how to implement this in Molly.jl, which is not the intended use of the package. So in some sense I will be reporting my user experience in using Molly in a slightly not intended way, which turns out to be quite easy. And then I'll talk a bit about some more prospective work we did on a new method to compute transport coefficients, again using Molly, and we discovered some interesting properties. Okay. So when you have a molecular system in thermodynamic equilibrium, you have some time symmetry in the dynamics at the microscopic level, which means that microscopically nothing happens in the system. You're basically static and you observe no flux. Okay? But if I perturb the system with a non-equilibrium force, for instance with a non-conservative force, I will induce some non-reversibility in the dynamics. I inject some energy, and as the energy is dissipated, I will create some flux. Okay? And the way this flux is described usually is through a constitutive equation. So think of Fourier's law of heat conductivity or Newton's law of viscosity. And transport coefficients in these constitutive equations are the proportionality constant between the flux and the intensity of the forcing. Okay. And those are important quantities to compute because the input into macroscopic models of matter, like Navier-Stokes PDEs, for instance, or reaction diffusion models. Okay? So here I illustrate a typical non-equilibrium situation where I heat up the system on one side and I make it colder on the other side, and this will induce an energy current to the system, which will be proportional to the energy gradient. And this proportionality constant is the thermal conductivity, what I want to compute. Okay. So I'll be a bit more precise about what I mean. So I'm doing molecular dynamics. In particular, we'll be doing stochastic molecular dynamics. So the evolution of my system is described by a stochastic equation, which is written here. In blue, you have the equilibrium part. So this could be, for instance, a Langevin dynamics, or maybe a dissipative particle dynamics. And then in red, I have a non-equilibrium part, which pushes the system out of equilibrium. Okay? So this is my non-conservative force. And then the magnitude of this force I will denote by a parameter eta. And this dynamics is stochastic because this W here is a Brownian motion. Okay. And for non-equilibrium system, this stochasticity is really important because you inject energy in the system. So you really need some kind of dissipation and fluctuation mechanism to maintain the system at a target temperature. Okay. Otherwise, you just heat up the system. And the non-equilibrium steady state of the system is simply an invariant probability measure under this dynamics, which I call mu eta. Okay? And in the special case where eta equals 0, I'm in equilibrium because I evolve under the equilibrium dynamics. And then my steady state has an explicit form, which is typically a Gibbs distribution. Okay. And then I need to describe my transport coefficient. So my flux is going to be given by the average value of a certain observable, R, which is a function of the state, under this non-equilibrium steady state mu eta. Okay? So it's simply a high-dimensional integral over the space of all configurations. Okay? But remember, this measure mu eta is not explicit, which makes this quantity hard to compute. And then the transport coefficient, I said, is a proportionality constant. So it's simply a sensitivity of this average flux, this macroscopic value of the flux, with respect to the forcing. Okay? So it's a derivative of this integral with respect to eta. And because this is a high-dimensional integral, this is a challenging property to compute. Okay. So I should mention we recently wrote a preprint on a review on the computation of transport coefficients. So this is a reference here. And there are essentially two classical methods to do this. The first one is probably the first one you would think about, is simply to put the system out of equilibrium by running the dynamics at some positive value of eta. Okay? And then you make two approximations to compute this linear response. So you approximate the derivative with a finite difference operator. This is this 1 over eta here. And you approximate the ensemble average with an ergodic average, so an average in time over the trajectories of your dynamics. Okay. And you can show this estimator as a variance which grows like eta to the minus 2, okay? Which means that if you have a high value of eta, you have a low variance. But on the other hand, you introduce bias because you have some non-linearities in your response. So you want to take a small eta to have a non-biased estimator, but then your variance grows. Okay? because you have a high noise to signal ratio. So another possibility is to use the Green-Kubo formula, which is a rewriting of this coefficient I'm after, in terms of an integral of a time correlation in the system under the dynamics at equilibrium. Okay? So I can relate the fluctuations of some correlations to my linear response. Okay? So this is an average over paths of the equilibrium dynamics. And this thing I'm correlating against is called the conjugate flux observable, which is some explicit function of the state. Okay? And so to estimate this, I can simply take an average over many paths of the trajectory and truncate this integral in time. Okay? And again, I have some bias variance trade-off, which is related to the time I choose to truncate this integral. Okay? And also there's some other method which relate this linear response to relaxation properties of the system. So when I push the system out of equilibrium, or I stop the perturbation and I relax back to equilibrium. And again, this gives you some integrated correlation to monitor. Okay? So first, I will implement those two methods in Moli. So I want to talk about the example I will use all the time, which is this computation of shear viscosity. So to do this, I will push the system out of equilibrium by imposing a shear flow. So I will push on the atoms in the x direction according to a certain forcing profile, given like so, which depends on the y position, for instance. And then my system will respond by having a certain velocity profile in response. So I push, the velocities will sort of align. And to monitor the intensity of this response, I will look at the Fourier coefficient of this velocity, okay, which I approximate with this empirical average. So the picture is the following. So I push on the system according to a sinusoidal profile. And the intensity of this forcing is given by my parameter eta. Okay. So let's go to Moli. So Moli is a Julia implementation of molecular dynamics. The main developer is Joe Greener from Cambridge. And the main focus of development and starting point of Moli is really its differentiable simulation capabilities, which have been used, for instance, to parameterize force fields for biomolecules. So here I have a simulation of a biomolecule that you can run on your laptop. By now, it has really a growing number of features, which make it actually a viable package for MD. And it's compatible with the broader atomistic simulation packages. And it supports GPU acceleration in a back-end agnostic way. Okay. But the main property of Moli which interests me is really its extensibility. So it allows you to basically implement various custom components of the simulation pipeline, including custom interaction terms, loggers, and simulators, which I will all use for my purpose. Okay. So first, I'll show you how it looks for the implementation of these classical methods. So here I set up a system in Moli. So I will define my physical constants. So here I'm interested in computing the shear viscosity of liquid argon. Okay. So I have the mass of argon, some parameters for my potential. For my potential, I will use a very crude model, which is a Lennard-Jones Perworth potential, my temperature, and so on. And then I specify the system. So the system is a periodic boundary, a number of atomic coordinates, some velocities, some atoms, some interaction terms. So here I have a Lennard-Jones interaction term, a neighbor finder, which allows Moli to efficiently compute the interactions, and then an integrator, which tells Moli how to advance the state of my system. Okay. And here I will use just Langevin dynamics. Okay, so then you construct the system, and I'm interested in the Fourier flux. So you have to define an observable, which is simply a function which takes the system and then outputs a number. Okay. And once you have your system, you can run with this simulate function. Okay. Now I implement my first method to compute transport coefficient, which is this non-equilibrium molecular dynamics method. And what this requires is really one thing, which is a custom interaction term. Okay. And so to define a custom interaction, what you need is a type and a method to compute the forces. So it's this atoms calculators.forces function for which I define a method. Okay. So here I define my shear forcing type, which has a certain shape of the profile and a certain magnitude. And then for my forces, I just tell Molly, for atoms calculators, to push an atom I in the x direction according to the y position, or to the value of the force profile in the y position. Okay? And I do this with the sinusoidal profile. Okay? And finally, I want to record my Fourier flux along the simulation. And to do this, I can just add a logger. So Molly supports the logging of arbitrary observables through this general observable logger construction. Okay? So now I construct my NEMD system, and I just simulate it with my simulator, again with simulate. Okay, and then for green cubo, what I need is really a correlation logger. So Molly supports a time correlation logger, which supports the logging of arbitrary time correlations between observables. Okay? So I just need to construct my conjugate flux observable, my SF, I told you about, which has an explicit formula, okay, which I didn't tell you about. And then I construct my time correlation logger here, which takes my two fluxes, the types, for efficiency reasons, and then a correlation window, which tells me for how long I will monitor these correlations. And again, I just construct my system and simulate. Okay, so this is fairly simple implementation of NEMD for a package which was not at all intended to do this. Okay. So I do this experiment. So here I use a very small system of 216 atoms. And you see the following. So in red, I have my NEMD estimators of the shear viscosity. And here you can see this bias variance trade-off quite clearly. So if I force a lot, I have this bias, okay, which comes from nonlinearities in the response. But on the other hand, if I take a small value of the forcing, then you have a lot of noise in your estimators. Okay. Green cubo is unbiased, and also at equilibrium, so this green guy here. But it's actually not very good, because so here I run green cubo with 5 times the budget of all the red points. Okay, and it's still quite noisy. And then blue have this experimental value, okay, but here I use a very simple pairwise interaction model and a very small system, okay? But already you get some qualitatively pretty good results. And I run this on a cluster of laptops of students at a summer school. So we had students compute in parallel and then push everything to Google Sheets and do this in one afternoon, basically. So this is one afternoon of computation on, 30 laptops maybe, and on a very small system, and the results are not so good. So in practice, these types of computation takes many weeks, and so really the goal is to find variance reduction techniques. Okay. So now I introduce the main idea, which is fixing the flux. So macroscopically, I said that the forcing on the flux was related by a constitutive equation. Okay, so the flux is proportional to my linear response times my forcing. Okay, and what NEMD does really is to fix the forcing and then measure the response along trajectories of the system. Okay. But of course, you could have another microscopic model where the reverse is true. Okay, if you just pass alpha to the other side, the analog is to fix the flux, and then measure the average forcing you need to sustain this response. Okay? So it's another microscopic model for the same transport phenomenon. And this idea was already imagined in a deterministic setting by physicists Vincent Morris in the 80s. Okay? So the picture looks something like this. So on the left, you have this NEMD method where the forcing eta is fixed, and I monitor a fluctuating response. And on the right, I have a fixed response in red, R, and I monitor a fluctuating forcing. Okay? And so the difference is the signal which I wish to estimate. Okay. This is from a real simulation. Okay, and so the mathematical translation of this idea is constrained stochastic dynamics. So I recall my NEMD dynamics here with an equilibrium part in blue and my non-equilibrium forcing in red. Now what I will do is I will replace this forcing term by a stochastic forcing term, which is given by a stochastic process, okay, lambda. And I choose this lambda to fix the response exactly during my dynamics, okay? So I have a constraint. And if you do some computations, you will show that this lambda is uniquely determined and has an explicit form like this, okay? It's an integral of lambda, a small lambda, plus an integral, a stochastic integral of lambda tilde along trajectories of my dynamics for some explicit values of lambda and lambda tilde. Okay? And then what is my linear response? Well, I do the same thing. I take the derivative of the response with respect to the forcing, except here the forcing is estimated. So I take the limit of the response divided by the forcing. Okay? So you can think of this as measuring a resistance rather than a conductance. Okay. Okay. And in some sense, this is quite similar to the duality between the canonical ensemble and the micro-canonical ensemble, if you know. So in one ensemble, you have the energy which is fixed exactly. On the other hand, on the other, you have a quantity which is fixed on average by the ensemble, which is the energy and the temperature. Okay. And now you notice something in this estimator, is that I take the ensemble average of lambda, which is only the term on the left here. Okay? Which means I discard actually this term, which I know has average 0 on average because it's a stochastic integral against a centered process. Okay? So what this means actually is that I do variance reduction with the control variate for free. I use this stochastic integral as a control variate, and I just discard it. And so in Molly, you can implement a family of integrators for this constraint dynamics in about 100 lines of Julia. And what you need to do is to implement a custom simulator, which means implement a type, which has the parameter of your dynamics, and then a method for Molly.simulate. Okay? So again, like the loggers, like the interactions, every part of the simulation is customizable. Okay. So the first plot I want to show is a comparison between the two methods for 1,000 argon, liquid argon, and stable liquid argon particles for these finite difference estimators of these quantities. Okay. So the good news is that it works. It seems to work at least. So in blue, you have this constant flux method. So here I divide the estimated response over forcing on the y-axis. And you can see the linear regime is this horizontal asymptote. Okay? And so the two dynamics agree in the linear regime. And again, you see this variance explosion when you have a small forcing. Okay. But what was more surprising, so this is already enough to convince us that this is actually a viable method to compute linear responses. But what's more surprising is that even in the non-linear regime, you still have an agreement, really, all the way between the two methods. Okay? Actually, we don't expect this to be true for any system. You can find the explicit counterexample of this property. But for physically relevant values of the force and the response, we expect this to be true in the thermodynamic limit, okay? When you take the number of particles to infinity. And we expect some kind of equivalence of ensemble results for these non-equilibrium systems. Okay, and the better news is that it works quite well in the sense that the scaling of the variance of my estimators with respect to the number of particles is better for this constant flux approach than for my NEMD method. Okay. So for NEMD, you get a scaling of the variance of like n to the minus 1, and for this constant flux, like n to the minus 5/3. Okay, and this is an interesting property because what this means. So for instance, if the scaling is n to the minus 1, because the computational cost of simulating a larger system grows linearly with the system size, it means that up to a point there's no advantage to simulating a larger system, because those two effects compensate. But for this constant flux approach, actually it's more efficient to simulate a larger system, which is quite good news because codes are good at simulating larger systems, because you can parallelize the computation of interaction terms. Okay, so this is true if the cost of communication between the subsystems which comes from this lambda is not too large. Okay. And for this shear viscosity, actually it turns out to be the case. Okay. And also see that in a recent paper, these results were replicated for dissipative particle dynamics, so they found the same scaling for the variance in some shear viscosity computations. Okay. But we don't understand why theoretically at all for now. So I'll just conclude. So transport coefficients are hard, both computationally and mathematically to analyze. And we need to develop new methods. And I'm a mathematician, and I don't like to mess with large legacy code bases. And we also need to test our methods beyond the simple low-dimensional systems to understand if they have a chance to work in really realistic conditions. And here Molly really helped us to bring this algorithm closer to computational reality and to understand these properties much quicker than we would have otherwise. Okay, and on the perspective side, we have lots of theory to do to understand this method. So this equivalence of non-equilibrium ensemble results are still being explored. And this variance scaling is really not understood at all for now. Okay, so thank you very much.
Questions?
What is the largest number of agents have you ever considered?
Sorry?
The number of agents, number of
particles?
Particles, yes.
About 10,000 or so.
Okay.
Yeah, I have a question regarding your interaction with Molly.
Mm-hmm.
How many lines of code did you actually have to change inside Molly?
Right. Zero.
Zero. Okay, that's, yeah,
well,
because I mean...
okay. I would be lying if I said I did not implement this time correlation logger. But otherwise, okay. But this is not the only use
So
case.
10. So 10 lines.
But this is not so... for the only use case of these correlation loggers is not for non-equilibrium simulations. So there are use cases for this, for instance, to put error bars on estimators and so on. So yeah, modulo despact, 0.
Any other questions? I have one about the liquid argon estimation from the Lennard-Jones, about 15% deviation. 15% is not something negligible. Like how?
It's not negligible. Yeah, sure. But you have to consider higher body order interactions probably, and larger system sizes as well. So you have several biases here. One that comes from the interaction model. Okay. So my point was not that Lennard-Jones potential is very accurate, but it's really that the two methods are consistent with each other. But there's a finite size bias that comes from the fact that I have a small number of molecules.
So it's actually a nice surprise that Lennard-Jones works. good enough to have an agreement.
Yeah, I mean, it's a model that's used by practitioners.
Yeah,
so.
Makes sense. Do we have any other questions? If not, let's thank the speaker again. And please, the next speaker set up, and we will start a set of short talks, so 15 minutes each. From Tokyo Metropolitan University. And first, thank you for making the long way here.
Yeah.
And please, the floor is yours.
Thank you for the introduction. I'm also my talk is also that thermoelectric transport, but the target is not a liquid or not a molecule, but my target is a crystal in the some kind of steady state approximation. So I'm my specialty is electrical engineering and sometimes treat thermoelectric devices. And this is some of the basic semiconductor textbook about thermoelectrics. Thermoelectric transport treat electrical heat and heat flow and electrical conduction and electrostatic field generation by the temperature difference. The important value is three values: Seebeck coefficient large S, and electrical conductivity sigma, and thermal conductivity. So we in this talk we discuss only the electronic part of the thermal conductivity. From the band structure, we can estimate, we can calculate, evaluate these three values. using these equations, these three equations. Here, the large L is a moment of the group velocity, product of the group velocity weighted by the distribution function and the energy, integrated over the k points. And n is the number of the eigenvalues, so that's a summation of the eigenvalue. This is called the constant relaxation time Boltzmann Boltzmann equation. And this group velocity is derived from the derivative of the electron dispersion from the electronic states calculation. And Bootstrap is de facto standard to calculate these three values. This was developed by the TUV group about 10 years ago, and this software is cited more than 10,000 citations. But this code is written in Python and compiled C++ extension, so it is sometimes difficult to set up this Bootstrap 2 in some kind of high PC, high performance computing environment that a compiler mismatch to the C++ and Python. And this code receives the DFT electronic state data by file. So there is no adapter for the DFTK Julia, the Julia's pure Julia density field theory electronic state calculation code. So I would like to simulate thermoelectric value from the DFTK. And instead of writing an adapter to the Bootstrap 2 for the DFTK Julia, I load a new Julia package to do a same algorithm to calculate three quantities. This is some code snippet to calculate the three value from the take result from the BASP, one of the famous DFTK code, and the calculation is two-step. One is the integration and one is the interpolation and the following integration. Integration part is already explained in the previous slide, but the original electronic state calculations, the number of the data is very small to calculate group velocity, so we need interpolation before doing the integration. And this my package called Bootstrap, not 2, Bootstrap Julia. It's written in a pure Julia using a FFTW and the SPGlib package. And there is no GPU usage, and a computation is performed by Julia native math. Using this very small 3 line, we can derive 3 quantities for thermoelectric transport. And this is some example to calculate these three values, starting from silicon diamond structure and the electrical dispersion, and the three values. Here, the leftmost figure shows three values as a function of the electrical electron energy. And this is a close-up, and I calculated I compared the result from the Python Bootstrap 2, Bootstrap 2, and my Bootstrap Julia result. And this is a calculation of, estimated at 300 Kelvin from the bus input, and the result is just the same. Relative difference is less than the 1 to the 10 to the minus 4th degree across the whole energy range indicated in this view graph. So, this my new package is developed by using some kind of reference text of the original Python Bootstrap 2 code. So then I goes to from the DFTK pipeline. This is a code snippet for the DFTK pipeline that the DFTK output Julia object of self-consistent data. And this one method, load DFTK, translate the DFTK object to the data to be read in my interpolation method. Just the same way, we can calculate. We can calculate thermoelectric quantities from the DFTK results. And this is the result from the DFTK data to the thermoelectric properties. And this is in the obtained by only 4 sentence code. Okay. So, and it is difficult to precisely compare the value of these three quantities to the BASP from the BASP computation, because the electrical computation condition is slightly different. But easily that the result is very similar to the DFT from the DFT result. And this is a benchmark that execution time as a function of number of K points, and roughly about 2 or 3 times speed up with respect to the Python's Bootstrap 2 computation. And very recently, I implemented a new interpolator. The original interpolator, Fourier interpolator, used analytic smoothing of the dispersion. It sometimes go to the long branch, so the interpolation gets some long values. Instead, I adopted the one year approximation that using a wave function, we created approximated Hamiltonian and diagonalized. So this one-year explanation does not go along cause a good correct branch. This view graph shows the group velocity calculated by the Fourier interpolator and one-year interpolator. And in the case of the one-year interpolator, thanks, the group velocity oscillate very much at the because in this branch that the dispersion getting some degenerate. This new interpolator can be used as a fast Fourier transpolator by use of the multiple dispatch of the JuliaCon. Okay, this is a summary source. So that my package can be used only just install this package. Finally, I have a poster session today, also for this package, and also the two another package I write. The short presentation is Friday, but the poster presentation today. So please discuss with me. Thank you for your attention.
Thank you very much. Before we take one quick question, can the next speaker please come down and set up? One quick question from the audience, please.
Yeah, thank you very much for the talk. I was wondering on the Bootstrap side if you're also planning to take this further in the sense of integrating with phononic properties, going to these more advanced ways of computing transport coefficient, heat transport coefficients. Is that something you have on your radar?
Usually, most people use a very large number of the K points is enough. but I would like to try this one-year interpolator.
Yeah, thank you very much.
Thank you very much.
Please thank Professor Sugawara again and find him at the poster session.
Nice to see the FTK use it.
Our next speaker is Bruno Plumens from the EPFL, and he will talk about algorithmic differentiation and error control with DFTK. Please, Bruno, the floor is yours.
Does it work? Oh, nice. Yeah, so I'm going to talk about DFTK again. And I wanted to talk both about algorithmic differentiation and error control. But since I only have 15 minutes, I will mostly talk about AD. But that's fine. So this is work that we did with Michael, who's here, and with Niklas, who is not here, but actually did most of the work, plus the first version of these slides. So thanks to him, and he's also the first author on our paper. So what's the context here? So the context is ab initio modeling. And the basic idea is that we would like to go from the structure at the atomic scale to materials properties. So why do we care about this? Basically, this allows us to discover new materials on the computer by just going from some candidate atomic configuration to some properties, and then we can measure those on the computer much faster than we could in a lab. And the workhorse method for this is density functional theory, which takes as inputs, let's say, the atom types we have, where they are, and for materials, we have a periodic box, so we also need the dimensions of the box. And from there, we solve basically where the electrons are in the material, which gives us the electron density, and then from there, we also get a total energy, forces, etc. And let's discuss what this looks like, let's let's say more mathematically. So we have some parameters, and we have to find the ground state density matrix. So this is basically what encapsulates the electronic state. It's this variable p, which minimizes a certain energy. And if you work out the optimality conditions, you end up with this nonlinear eigenvalue problem. So we have to solve an eigenvalue problem, except that the matrix H, the Hamiltonian to be diagonalized, depends on the eigenvalues. And so typically we solve this with a fixed point method. So we assume we have some p. This gives us an H. We diagonalize it. We update the p, and we repeat until we have converged. And we can also write this very compactly as a matrix function, but this doesn't help us solve it, of course. And I will talk specifically about plane wave DFT, which means that we have a very large basis. So we, P is a matrix, H is a matrix, but we never do any explicit matrix operation. It's always going to be matrix-free. Matrix-free Hamiltonian applications, matrix-free iterative diagonalization, and around that, an eigensolver. So this is what DFTK does at its core. So we'll have a talk later about this, so I'm not going to spend too much time on this slide. The main, maybe some things to mention is that DFTK is fairly easy to use. That's one of its selling feature, and easy to extend, and that it also has AD support. And I'll discuss a bit now how this is implemented. But first, let's have a quick example. So if this would be copy-pasted from a file called example.jl in our repository, it's kind of the simplest run you can make, you can run. And basically, we kind of have a few steps. We have the first box is the setup of our problem, where the atoms are, what kind, etc. Then we have the core solver in the middle, which is the most expensive part of the computation. And then depending on what we want to do with it, we have a few functions that we call down the line, so depending on the kind of post-processing we care about. And now, why do we care about derivatives? Well, it turns out that I told you in the beginning we want to measure properties on the computer, and many properties that we care about are, in fact, just derivatives. So for example, I don't have to explain what exactly the properties do or what exactly we differentiate, but if you differentiate, let's say, forces or polarizations or stresses with respect to different variables, you get different properties that are interesting. So we have been able to compute these with DFT for, let's say, 40 years. And the core challenge is to basically differentiate the solver. So the fixed point solver. And the theory that does this is called density functional perturbation theory, or DFPT. It's very established. You can see this is a review paper from 2001 at the bottom. It's quite a common method. And if we write it very compactly, we just take our equation that I had on the slide before, and then we differentiate, we rearrange, and we end up with this. But this hides quite a bit of complexity. It hides the fact that, so okay, you see we have a matrix to invert, so it's going to be a linear system. But inside, there's this chi0, and in the chi0, actually the chi0 is a derivative of an eigensolver. So we have a complicated inner conjugate gradient solve to deal with this. So it's actually quite complicated also mathematically. And there has been some recent work building on top of the FTK to improve the algorithm, improve how it's done in terms of preconditioning, performance, etc. So what does the workflow look like? What is also done in other codes? You write this green term by hand, painfully. Then you give it to the solver. And then you write the derivative assembly at the end very painfully, because you have to deal with all combinations of the post-processing quantity A you care about and the perturbation theta. So that's why many codes typically have only some of those derivatives, not all of them. And so really the core solver is, you need to be very careful, and this we wrote by hand in the FTK. But the main idea of this talk is that the other things we just let AD do. Just let AD take care of all the combinations. So if I go to my code example again, basically what would be the blue boxes we give to AD, and we just use the FPT for the core solver. So how do we actually do this in practice? So this is all going to be forward diff, and we call the corresponding framework AD DFPT, which combines the two. So this, again, the three-stage pipeline. Everything blue is done by AD. Everything purple is done is a DFPT. And we basically define a forward diff rule. So when you are about to call the STF function with duals, we say, OK, remove all the duals. Let's do our STF first. Then we do our DFPT afterwards. And then we repackage everything and give it back to forward diff. So this is how it works. And with this, you can basically do any output with respect to any input. So this is the framework. And now in the rest of the paper and the talk, I explain a bit what we can do. So we could compute some interesting properties with it. But what's also interesting is new derivatives that were not available in previous codes and that enable new directions. So one of them is, for example, gradient-based optimization. So here I take some semiconductor, and the key parameter is the band gap. And I ask, can I squish it to increase the band gap to some target value? And basically, you just write an objective function. So this, again, the function. You see in the middle, we have our iterative solver. Then we define a loss function called optim, tell it to use AD. It just works. So this is the full self-contained example for this. On a similar vein, something that's also quite interesting is learning something called the exchange correlation functional by fitting on data. So again, this is gradient-based optimization. And here we go one step further. We even optimize on the equilibrium geometry. So we have one more level of nested minimization. We can do the derivative. It just needs some unusual derivatives, which we can compute. So that's the idea. Again, gradient-based optimization. And I promised a little bit of error control, so this is also something you can do. If you have a model that has a parameter and you have a mean value and a variance, you can do a linear approximation, and then you get a covariance matrix in your output using the Jacobian. So this is all for error control. So I'm running out of time, so let's finish with a few takeaways. So the first takeaway is that the derivative of an iterative solver should be another iterative solver. For example, for a fixed point method, it's going to be a linear solver. If we have an iterative diagonalization, it's also going to be an iterative solver. And this one you have to do it quite carefully because of problems when the eigenvalues cross. And I'm happy to go into the details if someone has questions. And then if we do the DFT workflow, then it becomes DFPT. So my recommendation would be write it by hand, because it's quite tricky. But this is the only thing you would write by hand. And then combined with AD, we obtain AD DFPT, which gives us these end-to-end derivatives I mentioned before. The standard use case is properties, but maybe the more interesting thing is also new applications that are not available in standard codes. And I know here people really like reverse mode, so I have a quick note that this is forward mode AD. So it scales with the number of input parameters. And this is also how it was always done for property computations, for example. Maybe the takeaway here is that you can do already some things with forward mode. You don't have to go for enzyme directly, for example. But for high-dimensional optimization, you really need the reverse mode. So this is what Niklas is working on now. And the outlook is really learning a complicated machine-learned exchange correlation functional, for example. So that's all I have. Thank you.
Right. Thank you very much for the very interesting talk. We have time for a few quick questions.
Hello, yeah, thank you very much for the talk. I'm interested, so you showed this one picture where you can increase your band gap.
Yes.
So is it like, so you tell the program like your wished band gap and then sort of the derivative with respect to geometry, so you're changing geometry or atom type, or so what's going on?
Can you read the code with the function in the middle? Is it readable?
Yeah.
Okay. So this is a function that takes eta. So this is by how much we want to perturb the lattice. You see it builds a new model with the lattice that is multiplied by 1 plus eta, so expanded or contracted a bit. Then we do the DFT, and then we kind of compute the band gap. So you see we take the eigenvalues, then do a maximum, minimum, and take the difference. So it's a DFT band gap. It's not like, of course, all caveats of DFT apply here. But as a toy example, you just write the property you care about. Yeah, and then below, we have a loss function. So this is in the second box. You see we have target minus what we compute squared, and then derivative.
Thank you. And can you get like trapped in some local minima or something? So like that the wished one is not acquired? Or?
Yeah, there's no reason why you would find a global minimum.
Okay, thank you.
Any other questions?
So how well does the auto-diff like DFPT approach compare against like standard approaches in terms of performance? Because I know DFPT is rather a slow process.
So the main bottleneck is the core solver, which we handwrite anyway. So this upper right equation. So hopefully, basically you have this core solver, which is as fast as in the other codes, or maybe a bit faster because some extra insights were applied. So maybe if that works well. And then in the post-processing, if you were really doing something quite heavy to compute in the post-processing, then maybe the 4-diff approach has more overhead. But normally it should be the solver, and then it's equally fast because it's handwritten.
All right, let's thank the speaker again. And we will move on to the last short talk of this block by Henry Snowden, now at the University of Göttingen in Germany. And Henry will be telling us about simulation of light-driven hot carrier dynamic and transport. All right, take it away, Henry.
Yeah, apparently. Cool. So thank you very much for inviting me here today. Last year, I gave a half-an-hour talk about lightmatter.jl, so I don't want to repeat everything I discussed last year. So I'm going to go over sort of the core basics of what it does and what it aims to do. And then I really want to talk about a certain use case where I found how simple mathematics really caused some computational challenges and made me revisit how I propagated my code through time in order to make it efficient. So why do I really care about light matter interactions and electron dynamics? And the main reason is plasmonic photocatalysis. I'm in the same group as Alex Spears, the talk you heard earlier. And so we're interested in chemical reactions on surfaces, and particularly ones driven by light. And there's many reasons for why you might be interested in this. One main reason that I like is that typically grant agencies like to fund sustainable things, so this is always a strong benefit. And surprisingly, we happen to have the same image you may have seen in his talk earlier. And here in this example, we have an experiment where we have CO2 reduction on either rhodium or gold. And in the case of rhodium, it produces mainly CH4, and on the gold, mainly CO. Now, this is a clear different result, but why exactly this difference occurs is a great interplay between many degrees of freedom and is something that experimentally is near impossible to determine. And so theory and modeling techniques are the real core workflow behind understanding what occurs on these systems. What do I mean by all this interplay of degrees of freedom? Well, here's a timeline of what might happen in a light-driven event. First of all, we have a laser hit a nanoparticle and create a plasmon. This is a correlated electronic motion and lasts only a few attoseconds, so very small time frame. And then as it decays, it generates hot electrons or excited electrons and excited holes. And these you can imagine as basically an electron that's absorbed a photon and gained 1 photon of energy. That's effectively what these are. And they live a maximum of about 100 femtoseconds. So now we've gone from attoseconds to femtoseconds already in our sort of time span we need to consider. As these start to bounce off one another and scatter, we now generate a heated electronic temperature. If you remember Alex's talk and the two-temperature model, this is at the high electronic temperature you saw, and this will slowly cool down and interact with the phonons, and therefore all equilibrate again. And at that point, once we've equilibrated with our phonons, is the point at which we're at the same state we would be if we just used thermal heating. So effectively, everything before then is purely only accessible through light-driven techniques. And Alex himself discussed all of this here, and so I'm really going to talk about this first part over here. So the way we do this in LightMatter.jl is something called the athermal electron model. This is an approximation of the Boltzmann transport equation that was also nicely introduced in its steady state form in the Boltzstrap talk. And what we do is we take an electronic distribution rather than a wave function or a density matrix due to simplification, and we separate it into two main parts. We have this athermal part that holds all these excited electrons and holes, and we have this thermal part that we can just describe by temperature, therefore making it a lot simpler to interact with. If we take this thermal part, we can imagine coupling it to a phonon bath. This is the two-temperature model that you all well know, and it just energy is dissipated via this coupling term, G. This is a very simple approximation, but it does a surprisingly good job at capturing the long time limit of what occurs in laser excitation. We simply need to couple this to this electron hole pair system via some scattering terms, and there's a reason I haven't expanded out any of this, and that's because this would probably fill the page. But most importantly here is that this electron-electron scattering term is incredibly expensive. You can imagine this as every electron interacting with every other electron, and this is obviously a very complicated process, and therefore is computationally intensive to solve. To do it properly, I think I calculated it to be a 12-dimensional integral, so not something you can feasibly do. And therefore, when we interact or propagate these equations, we have to really consider how often we need to propagate and evaluate such an expression. Now, this is sort of the core behind ATHEM. This is a model I created in my first year of my PhD, and it is only publicly available inside of the lightmatter.jl package. Does it work? Thankfully, yes. Here on the left, we have an experiment where they were doing electrochemistry, and they were looking to measure the rate of hot electron capturing by some molecule called CTP as a function of wavelength. And on the right, we take basically the excited distribution as a function of time and the LUMO of the molecule and calculate the transfer rate, and we get a pretty good qualitative match for such a simple model. So we can really capture all of this complicated quantum mechanics in a semi-classical framework rather well. And if you want to see the actual details that I've kind of brushed over here today, please have a look at the paper, or you can feel free to come talk to me. I'll probably be at the NQCD poster for the most of the evening, so feel free to find me, and I can talk about this or NQCD. Anyway, unfortunately, everything like this experiment has so far been done on monometallic particles where I get to treat them as almost a single point in space, and everything is nice and simple. But in the real world, the interesting systems are not monometallic, nice nanoparticles. They look something more like this. And as you can see, we have multiple different materials and multiple different configurations. And so now we have to consider spatial non-uniformity in our system. And when we have systems with a spatial degree of freedom, we need to consider our degrees of freedom moving around. How do our electrons flow? How does our temperature flow? This kind of thing. This is done via two rather simple equations. One I'm sure you've all seen before. It's just sort of fixed law, standard diffusion equation of temperature. And the other is ballistic electron transport using the group velocity that was, again, nicely introduced earlier. And I've used these equations plus the ATHEM model to look at systems like this. These are Janus particles, where we have a gold on the left and palladium on the right, as well as looking at how the electronic structure of the surface changes the light response. I'm not going to go into any of that detail today. What I really wanted to focus on here is that these equations really don't look too bad. It's the second derivative of a temperature and the first derivative of a distribution multiplied by a velocity. All of this is rather simple mathematically. So if I had to do a single point calculation, this is our 0D, you can see using the standard Chris Rakalkas recommended integrators that SIT5 performs complete simulation in about 0.02 seconds, whereas an implicit solver like Rosenbrock 23 takes 40 times longer. So a great cost increase, but of course you wouldn't need such a system, as the normal 0D equations are nice and non-stiff. As soon as we introduce transport, SIT5 now can no longer complete the simulation. I left it running as trivially parallelizable as I could get it for about 2 weeks, and it got about 3 femtoseconds into the simulation. And this was adaptive time step and everything I could do. You compare that to the fact that Rosenbrock now gets it in 6 minutes, so clearly something Even though our addition of our mathematics was simple, the computational cost has completely ballooned, and how we approach any level of propagation has completely changed. And this is really what I want you to get away from this talk, not necessarily my code, not what I do, but really that when we add even some simple math, we have to look at our calculations and our computations and completely revisit what we are doing and are we doing the best way we can. How do you solve this problem generally? Well, stiffness, if you're not aware, is how I like to consider it, is a measure of propagation complexity. Basically, how hard is it to go from time t to time t plus dt? And in the case of Euler-style propagation, it's bounded by the eigenvalues of the Laplacian. I'm not going to go into too much details. And these have a 1 over spacing squared dependence. Basically, if I want to double the resolution of my simulation, I have to drop my simulation's maximum time step by a factor of 4. And so you can see, as we make our simulations more and more accurate, down to the atomic scale surface difference that I mentioned earlier as one of my applications, your time step would have to get incredibly small. I mean, far below zeptosecond. Whereas the Rosenbrock methods, they use something different, where they actually calculate the Laplacian explicitly, and this is now a much more stable method to propagate through time. However, it comes with a cost. This is a matrix, and it's a matrix of the order of your number of degrees of freedom squared. Now, I have an electronic distribution. This is something I solve on a grid, and has about 1,000 energy points per spatial degree of freedom. So if I have 1,000 energy points and 200 spatial points, this is now a very big matrix. And in order to evaluate this matrix, if I'm going to perform an electron-electron scattering at every point, I also calculated that, and I think just about the end of the universe comes first, depending on accuracy. So clearly, this is not a feasible approach. And the solution to this is really IMEX methods. These methods are where we separate our problem into two components. Our non-stiff part, this is the part that we knew worked nice and well in our 0D, and the problematic bit, the bit that suddenly made everything nice no longer work. And in our case, here's all the equations again, nicely wrote out with our transport added. We know that our 0D, our explicit component, is just here in blue. It worked in 0D. It should work just fine in 1D. And we just need to treat these transport components slightly differently. And now we have another nice feature that our transport is tridiagonal if we use central finite difference. And this greatly increases the performance of our implicit calculations and actually brings the scaling down to O to the n. So we can separate our problem into two components and now get sort of the best of both worlds. What does this do? Well, on a single D sort of simulation or a single point simulation, using a solver such as KenCart4 does increase the computational cost by a factor of 2. This isn't great, but it's a small price to pay for what is about to come, which is all of a sudden we've dropped by a factor of 20 in our performance for this 2 nanometer spacing simulation. And so now we are much more performant. And if we half the spacing, all of a sudden our Rosenbrock has increased by a factor of about 1.5, whereas our KenCart4 simulation barely increases in computational cost at all. So effectively, we now have much cheaper simulations and much better simulations with minor changes to how we propagate our dynamics, just some changes in lines in ordinary diffie-q. But really, it's all about thinking out of the problem. That's the key sort of message here. And so lightmatter.jl is the package that all of this has been done inside. It's powered by ordinary diffie-q, as I just mentioned. This package is incredibly powerful, and I owe basically most of my PhD towards these people and their incredible work that they've put in. And it basically utilizes ordinary diffie-q and some nice tricks to become the most flexible and performant package that can do these kind of simulations. And it's also the only open source package to include the ASA model, as well as all of these other models. So if you're interested in light matter dynamics, please give it a go and talk to me. I have so much time to code more things if you really want me to. Anyway, here's the code. And as a leaving point, while I ask any questions, here is an equation you might all see often. This is a common problem for where IMEX might be applied.
All right, thanks, Henry. Yeah, we have time for a few questions.
Thank you for the talk. It was quite interesting. I had a question when you're talking about light-matter interaction. Are you looking for a specific structure for the incoming light, like light with a special structure, like Gaussian beams or stuff like that?
So at the moment we have, so our light is modeled classically, so there's no like chirping or quantum mechanical nature, but within the code we can handle Gaussian beams, we can handle rectangular beams, and various other sort of classical approximations of the light source. But we don't actually propagate the electric field explicitly, basically.
Mm-hmm. Thank you.
Any other questions?
Hi, thank you. Apologies if I'm slightly misunderstanding when you were talking about kind of the problem of splitting up the differential equation system like that, because it resembled to me like some standard splitting methods that you see in numerical analysis. And so I was just wondering if you had investigated like some of the different splitting methods that exist for differential equations, because I know there's kind of a wide variety of like different ways that you can handle splitting it up like that.
There are, and I have, but unfortunately, one of the things I wanted to do with the code was make it reasonably flexible but fast, and the more complicated and efficient splitting methods also kind of force you down more and more rabbit holes of what your code has to look like and how it has to be structured. The code in the back end is a bit Lego blocky. Basically, every single part of the equation is completely user definable or anything. It uses symbolics basically all in the back. So I wanted to make sure it was nice and simple, so I went with like a simple summation split.
All right, let's thank Henry again, but he can't stay at the podium because we are about to start the panel discussion session. So, yeah, Henry is from a University of Göttingen as a PhD student, and now let's invite Professor Michael Herbst from EPFL. Michael is a faculty at the Mathematics for Matter group. And also let's invite Jorge from ASML. If you don't know, ASML is probably one of the most important companies in the world that really is the enabler of a lot of rapid developments of all the modern ML AI technologies. So yeah, this session is supposed to be interactive and also casual. So yeah, and I will let the panelists to do a quick introduction about themselves and also, thank you, and also the most challenging problems they're trying to solve in their daily work or daily life. And yeah, let's start with Jorge.
Yes. Okay, thank you. I have to say that I haven't used any molecular dynamics or anything since my bachelor's, so this was kind of refreshing. Well, I don't personally do any molecular dynamics on ASML, but I know that for the UV systems, we have this rarefied gas. So we call it vacuum, but it's not actually vacuum. We have this system over there, and it's in a vacuum because UV is absorbed by everything, air included. So we just lower the pressure over there. We call it vacuum, but it's not actually vacuum. And we have a lot of gas over there. So there's some, there's argon, I think, and there's some hydrogen. And we could use some of molecular dynamic simulations over there to understand how the properties of that work, especially in these very low pressures. Maybe some Boltzmann techniques will work. I don't personally do anything, but I think there could be some opportunities over there to apply that there. But if I would like to do that, I don't know where to start. So please tell me, if I want to do, where should I start?
All right. So yeah, I think, should I answer or?
Please, yes.
Yeah. Okay. So I think first some introduction probably. So yeah, I'm Michael Herbst. I'm the person running the MATMAT group where Bruno is presented on our density functional toolkit. And basically this is sort of what keeps us busy most of the time. Basically trying to come up with a density functional theory code that understands errors and is differentiable. And the current problem that I think I'm super interested in we are faced is how do we make sure that we can use, for example, data that is out there or data that we can generate to come up with physical models that are more accurate, because all the models are limited, and so basically going beyond that without having the costs explode is something many people are working on, and I think data-driven methods is something that has something to say, and basically that's one of the current big problems we're looking at. Yes. I don't know.
I also didn't introduce myself. I'm Jorge Vieira.
Hi, yeah, you just heard me speak. My general background is non-adiabatic dynamics and light-driven methods, obviously. Basically, I'm primarily interested in gas surface dynamics, where sort of the computational cost of our standard methods like DFT or CCSD or any of that scales to the point where things are no longer possible. Ab initio dynamics no longer is feasible, and nor is even ab initio electronic structure when it's done on excited states, etc. Trying to do that with thousands of atoms or thousands of electrons is, basically impossible. So really, I'm interested in what approximations can we take in order to make interesting systems still computationally feasible, and how we can get the most out of what we have via coupling to machine learning, that kind of thing.
Maybe you repeat the question, because
maybe also I didn't know I have to introduce myself, so I thought it was irrelevant. So hi, I'm Jorge Vieira. I studied chemical engineering in Mexico. However, I was always very involved with the theoretical chemists, and then over there I started working on molecular dynamics. Also applied that a little bit to chemical engineering. Then I studied my master's in material science and engineering at MIT, and then PhD in applied physics, and ended up at ASML doing microfluidics, so all over the place with simulations. So I have experience running simulations on, DFT when was the new kid in the block, so I'm that old. But also run the finite method calculations and some more kind of continuum dynamics or approximations for surrogate models, especially for embedded systems. So that's my background. Going back to my question. So I have a molecular dynamics problem in the industry. In this case, I have some rarefied gas, argon, hydrogen, and I want to make a simulation. Especially, I want to see if things will go ballistic or if something will react with tin. In this case, nobody knows why sometimes this is reacting. So where would I start with the Julia ecosystem trying to make a simulation like that?
Yeah. Let's invite the panelists to give them a first attempt first.
Okay, I'll have my attempt. So where I would basically start is trying to keep things simple, because it's very easy to burn a lot of time doing expensive things that don't get you very far. So from my experience, we work a lot with MACE, which is a machine learning framework, and there's been a lot of work on foundation models, which are basically these models that give you an okay guess at energies and forces, within reasonable accuracy, straight out of the box. So possibly a good starting point would be throw one of these like foundation models onto your problem, throw a standard adiabatic dynamics, Born-Oppenheimer, and see if what you get is in any way reasonable. And if you start to think that it is, and then I would basically start iterating on this process. So first of all, I would work at the machine learning model from the foundation model is not going to be that accurate. So maybe we need to actually run some quantum chemistry calculations. That's where things like DFTK come involved. Optimize your machine learning model and build one that solves your problem accurately. And then run more dynamic simulations and see if you get a result that you would expect, basically. Because most of the problem with a dynamic simulation is going to come in how you describe the electronic structure, not particularly how you describe the dynamics.
Yeah. And I think what is interesting to mention here is that about maybe 20% of what you said is Julia at most. That's extremely optimistic. I would say 80% is Python or other random stuff. Because basically, I mean, all of this is a lot of orchestration. There's a lot of, running multiple jobs on a cluster, keeping track of this. So there's a lot of software that even goes into the overhead of keeping track of what's currently going on. And basically, the field is very rapid in the sense that, like, these foundational models that Henry just mentioned, I mean, They came out 3 years ago, right? And Amaze as the model that he mentioned, I think this may be 6 years, 5 years in this order, right? So basically this is the state of today. And if you're basically asking the same question at next JuliaCon, we will probably give you a different answer. So what I'm trying to get at is that in some sense, the idea to have our ecosystem in Julia and, that's what we're using, I don't think that's extremely realistic, right? We have to be simply acknowledge that this field is moving super fast and that the only way you can actually make this useful from any endpoint, whether it be Julia or Python or whatever, is to make sure that interfaces are there and these are interoperable such that everybody can talk to everybody. There are some projects that are going in this direction. I mean, the most famous project is called the Atomistic Simulation Environment, ASE, which also has inspired a lot of the work that we have done in the Julia MolSim. And in particular, there's some memorandum of understanding. So I'm also part of, for example, the steering committee of the ASE, so I have some first-hand insight of what's going on there. And there's some memorandum of understanding that there's stuff happening in the Julia world, but of course it's not priorities from that point of view. So what I'm trying to get at is, I think from our point of view as a Julia community, seeing what's going on in the general environment and trying to see how we can interoperate with them, that's probably a very important way to get also usable by, for example, people like you who actually have a concrete task and now need to use the best tools that are available, right? And only some of them will be in Julia. I think it's very unrealistic to think that all of them will be in Julia.
My question is like, where will I start? So if I have to tell you, when I was doing these kind of things at the university, there was no Julia ecosystem. It was like, okay, somebody had some Fortran code over there, and then you have to write it yourself. Not even Fortran 90, it was Fortran 77, very painful. You have to modify some code at work, and then you do the first Monte Carlo simulation over there, and something like that. And then if you were lucky enough to be in one of the teams that had a Silicon Graphics machine, imagine how old, they were running this, what was it, Sirius 2 software, and you have to learn how to use it, and I was not one of the lucky ones.
No idea what this is.
Okay. It's old, it's old thing. But the thing is that at the time, it was like that. Nowadays, we have a lot of nice ecosystem, even if it's a smaller one in Julia. Now you can just quickly go and drop in and see what's off the shelf. You can immediately interact with other people, so that makes things even easier. However, there's a lot of availability, and I don't know where to start, right? So you have a problem. You already said, okay, look at your data, try to do some data-driven approach. I personally prefer first principle approaches.
Good choice.
Good choice. But I will not know where to start. So the only package that I have tried, by the way, is Molly. It's the only one I have tried. So I don't know what else out there. And sometimes to read the documentation of some of the packages, I already need a PhD on that topic to be able to read the documentation, which, well, I do have, but not on on those topics.
Sure.
So I don't know where to start. So that was my question. So my colleague will try to do something. We'll go to the Julia MolSim page, landing page, and then say, I don't understand it. I will do something else. So that's where my question came from. So I don't know how.
So Michael, are you confident that we can straight away just try to solve very realistic problems with the
Oh no, I
existing
don't
tools?
think so. No, I have to be. I mean, not with just Julia tools. I don't think so. Yeah.
And
I think if one start, I mean, as Henry suggested, if we start with one of these classic foundational models, which actually have first principle quality.
Okay.
So don't think of them as data-driven. I think they're really pretty good these days.
Okay, very good.
I think with that and an appropriate scaffolding, Python-based, I guess, unfortunately, you can have some first ideas and then basically see where you take it from there.
Well,
yeah, that will be my starting point.
Whatever is
honestly.
fast in Python is not Python, so we can interface with the
Yeah,
backend anyway,
sure,
right?
Sure.
Yeah, any thoughts from the audience? Anyone have any suggestions or brave enough to say, oh, I can solve this problem? Yeah.
Yeah.
Or if you have other gripes about the ecosystem, for example, that I haven't mentioned.
Yeah, okay.
Thanks. Maybe going a bit in the same direction, because it seems like Molly is doing molecular dynamics, and then you can, in principle, when you have MD code, plug in any kind of electronic structure code. And I mean, I'm not a user yet, let's say, and I'm wondering a bit, going in that direction, can I take Molly and use one of the foundational model you mentioned, and then without necessarily leaving this framework, iterate to get more accurate results?
Yeah, it's a good question. I have no idea. Noe, do you know? Okay. Do you know?
Yeah, so you can interface with ACE potentials. So those are linear ACE models, basically. And I guess we heard about a maze wrapper in Julia. So if it returns the forces, you can plug it into Molly. So
to add a little bit of sorry.
Yep, sure.
Yeah, to add a little bit of context, I mean, the whole point of starting this Julia MolSim a couple of years ago was exactly to make this possible, what you have essentially alluded to, that one, starts with a simulator like Molly, and then one has like a library of potential force suppliers, calculators as we call them. You could just kind of plug them in and it runs, and you start with a foundational model and then switch over to, I don't know, DFT or whatever. So this was the intention. I think to some extent it works. But again, I mean, since nobody is doing this essentially as for a living, I mean, developing these interfaces and implementing kind of the compatibility, and the field is so incredibly light speed fast, the most relevant today models in general would not be available, I would say. You would in general need to go via Python. But I think it's feasible. Like I would, because I think the short answer is, in principle, it would be feasible to use Molly and couple it up with one of these foundational models. Yeah.
Yes. So I wanted to ask again if you could describe the problem a bit more. So you said you have argon and hydrogen, and this is some sort of in some gas phase, and then on top of some surface, or?
Yeah. Well, so UV systems that work on vacuum, not really vacuum, it's low pressure, and they have some rarefied gases there. So what I want to know is like, okay, if I want to have a simulation like that, what will be the limits of the ecosystem? What can I simulate for those kind of conditions?
Okay, but if it's like vacuum, so you have very less amount of molecules, just let's say hydrogen and argon, so those are relatively, like, I don't know if easy to treat, but you can actually use some high-level methods to do some potentials and then see hydrogen gas, how it's interacting with argon and stuff, and then you can even use, I don't know, a couple cluster level for those interactions, that's no problem. And then you can, again, feed it into some force fields, as you said already, and then you can run some force fields, and then one can sort of say almost ab initio accuracy.
Can I simulate if hydrogen reacting with tin, for example?
So with tin, so is it like a surface or something?
Yeah, it's all over the place, yes.
Okay. Okay. Yeah, so there are also solid state codes. I mean, okay, so of course DFTK.
Yeah.
What I also know, but this is not from Julia community, but generally there are also some surface models. And for example, what you could do, let's say you do this hydrogen-argon interaction with some ab initio methods in the gas phase, and then you can also do some atomic interaction with the surface, and then also make there a potential of, I don't know, DFTK, some other methods, I don't know. And then you have like all of the required potentials, I would say. For example, I mean, well, I don't want to make advertisement, so where I'm from at Humboldt University, there are also some code for actual surfaces, or if you need like slabs or whatever you have, like solids, or also on ab initio levels, and then you just make the potentials and then force field fit it or machine learn it, or yeah, what you like.
How much of this works today?
So like
out of the box.
Out of the box, if you give me so hydrogen and argon, and I can make you potentials. This works today now.
Let's say hydrogen and tin. So if
sorry. Okay,
yeah.
so hydrogen and tin. This also works today, so I can start some calculations and then, well, again, so this is not with Adam Koif.
So you have the scripts ready.
Well, I mean, it's some, I mean, so if you give me the tin, then you have to give me the, of course, configuration. I don't know, the slab, the cut, and then you have to give it to me. And then I have to, yeah, well, make a plot where I do like hydrogen and then, I don't know, do some distances to the surface, let's say 10 angstrom, 5 angstrom, 2 angstrom, whatever. And then I can calculate it on the level you require. We have also a couple clusters, let's say in a fragment. You give me a tin or whatever. And then...
You mean samples?
No, just give me the geometry. So you have to tell me what kind of tin it is, right? I mean, I don't know in what configuration it is.
Let me generalize the question. That what matters more for you, the accuracy of the model at kind of a static condition, or the dynamics of, you know?
It will be, in this case, it will be dynamics. So the problem that I have in mind is that, the UV systems have this tin source. We basically make these small droplets with tin, and we fire with a very high power laser, and we just evaporate it. And then tin is all over the place. Yes. So, and then in particular, they go into one part of the system called the collector, and that part is usually overflow with hydrogen. And then we got rid of the tin that accumulates over there, and we more or less know the process conditions where it's gone, but we don't have any simulations.
So, Henry, how many PhD projects is this? What do you think, 3?
Yeah, 3 seems about right.
So just to give you an idea, so I think this is about 3 PhD projects.
Oh,
research of 3 PhD projects. Yeah, sorry. Yeah.
No, so I did not understand that there's a laser source which is somehow evaporating tin, and then tin is mixing with hydrogen and then going to some source, right?
I didn't explain that, yes.
Yeah.
So what I was talking about, so if you have some sort of adsorption on the surface, you have some interactions of gas, but of course with lasers, so
the fact is that we evaporate the laser, the tin, it deposits on some surfaces, and then to get rid of the tin on that surface, because it's just contamination, right? We just overflow with hydrogen. So, yes, and then to get rid of the tin, we throw hydrogen, and we know more or less the process window, but there are no simulations behind it. So it's just more empirical kind of thing.
I think, I mean, a bit along the line what Charlotte said, one basically has to identify sub-problems. Like each of these things what you just described is probably 1 or 2, maybe even 5 separate simulations that zoom in on one particular physical effect, and then one chooses the right kind of methods, like for example for understanding the binding of the hydrogen with a tin on some other surface, like silicon surface. That's, I think, a couple cluster and solids type of problem. Then for the laser, I think Henry's type of methods are really the ones you would go for, with again multiple simulations, changing the size. So this is why I, half jokingly, half serious said this thing with the 3 PhD students. I mean, this is really a big endeavor that we're looking at.
You have topics now.
So
yeah.
Then clearly, we have identified the gap. So when you go back to your headquarters and report on, the progress here or the current state of Julia Molson, apparently that we need 3 or plus PhDs. Would you suggest to your superior that we just hire 3 postdocs and to work on this problem straight away, or would you prefer to, establish a connection with a university or research group to,
I personally don't work in UV, so I could not have those kind of things, but I could suggest someone who we can refer to. So that could be a possibility.
So, to rephrase it, what's a corporate mindset of solving this problem? Because you could, put in a lot of resources, but investing a lot into your own company.
Oh, no. So we have collaborations with universities, and several master's theses and PhD theses come from these collaborations. Usually, we have a problem, we want to understand a little bit more. We have a collaboration usually with an Eindhoven Technology University in Eindhoven, so that's easier for us. And from them, say, okay, we have this very small particular system. We might want to know a little bit more about this, but this is not something that we will research. It's something more like academic research, but we would like to know, and sometimes there are some grants or collaborations that come after that. So that's usually how it works. In my previous, in my group from my PhD studies, we have several projects like that.
But that's only true for the projects that it can wait for a few years or for the three PhDs to graduate.
So things that we have that need to be solved, like right now, we just investigate and we try to solve them, and usually in a very pragmatic way, because we need to make the system work, right? But at some point it's like, okay, we know how to tune some knobs and it works, but we don't understand why it works, and that's when we approach universities.
Yeah, that makes sense. One more question, and you know, we have a lot of, you love first principles approach.
Yeah, that's my personal thing.
But that approaches take time. Meanwhile, there are also cross-grain, some rougher models that can give you an answer quicker. Which way would you prefer?
Well, personally, the fast one.
That's a very clean answer. Yeah, please. Yeah.
Yeah, so I would also be interested, I have some question. So like ASML, so do you occupy some theoretical chemists? So like, do you have some people employed or theoretical physicists, right? So like, or mathematicians?
So that's a hard question. ASML is a large company, so I don't know everybody. I personally have never met any theoretical chemist, but there are plenty of physicists. There's one over there, the sitting on the back, that works at ASML as well. We have a lot of mathematicians, usually working on numerical methods that can help us. I have had colleagues that were biochemists. Why they work in ASML, don't ask me. So some geosciences. So the problem with photolithography is that you generally don't study that at the university, and there are a lot of people from different backgrounds that just, you know, they start to like computers or they like calculations, and they naturally gravitate towards photolithography for one reason or another. However, there are a lot of chemical engineers. I have met a lot of chemical engineers at ASML.
So do you have a materials simulations department, like a computational materials development division or something?
Not that I'm aware of. So I used to work in another department, which was called defectivity performance. And over there, we analyze a lot of materials, especially things that are contaminating the system. So we have a semi-DX or X-rays analysis and stuff, just to see, okay, we have a particle of copper here in this wafer table. Copper is no.
But this is experimental, basically?
It's more experimental.
Okay.
Yes.
So no simulation people.
There are simulations, but very localized. So there are some fluid dynamic simulations that I know. There were people that were working on simulations on rarefied gases. That's why that's where the example came from. Sometimes they were studying desorption, because again, vacuum. And then it creates a lot of problems because all the materials that are in the system, they start to degas, and those can create some problems, sometimes create some cracks on the material. So we have some people doing some simulations, but it depends per department. So we don't have one particular place where all simulations will happen. So they are all sparse all over. We have one division, which is called research, where they will do more kind of things that are like, we don't really know this is going to be applied, but we might have the feeling that we might need this. So that's the research department that we have.
Okay. So one last question about actually Julia, so since you guys are here, and also I know there are ongoing works with projects using Julia for system simulations. So I assume I don't have to sell how good Julia is.
Well, why should I use Julia?
But apparently we still, you know, at least within the molecular simulation, there's a gap to fill, and a lot of tools are still, you know, in a different language, and it will take years to bridge this gap. So so what matters to you? Would you like think we should keep investing into using Julia, or we should try out these Python packages if it works better.
I mean, we'll try Python. Again, whatever is fast in Python is not Python. So I think we should try to make Julia backends for Python. Now with this Julia C that we have, we can just make, I don't know, Molly. Molly works perfectly fine in Julia. People don't want to use Julia, fine. Just make an extension in Python using Julia C, and then people want to use it from Python, fine. And then they will still be using Julia, just using a Python interface. So that will be what I would recommend.
That's great to hear.
Yeah. Or stick to Julia. That would be better.
Any other comments from the audience? Any last-minute burning questions? Ask anything. It doesn't have to be Julia Molsim related. Or if you have a great business proposals, it's a perfect time to pitch.
I mean, it's not directly related because, again, I'm new to the community here. But I was kind of wondering, and I may be biased because I'm from the X-ray community in a sense, where we have this problem that we compute stuff, it's very nice, and then we have a totally different code to compute how we can probe it experimentally. Typically, what is a spectrum, what is the photoelectron that would come out of it, and things like that. And I was wondering if there is anything with the ecosystem in Julia that could help kind of bring things together or not, or if it's something that have been discussed or thought here.
That's for you.
Yeah. It's a bit hard to say without knowing details, of course, but I mean, generally the whole point that we were trying to work towards is that at least any form of atomistic structures could be represented in a way that other codes could just basically tap from that without too much effort, not worrying about units and conversion and, this sort of thing. So that's, I would say, the minimal aspect. And then, of course, I mean, usually in specific domains, like, in Henry's code, there's a lot of details, like, different energy surfaces, how they interact, that stuff that in general Julia Molsim is not needed, and then they've built their own extensions on top of this. So I would say probably in your field it's similar. I mean, there will probably be some aspects that a general code doesn't have, and then, so in that sense, you're kind of still a little bit on your own. I mean, yeah, I don't think we have solved all these problems. I think there's still plenty to come, I'm afraid.
And lastly, any promise?
I should promise? No, I'm not promising.
Yeah. Okay, I think let's thank the panelists again. And thank you all for your input and getting this discussion going. And thank you, Jorge, for joining us.
Thank you for asking the great questions.
And now this time, Michael can stay.
Yes.
Of this afternoon on DFDK.
People can see my pointer, yes. So this talk is basically talking a little bit about what has happened in DFDK broadly in the past couple of years and trying to give you some hints, insights into the code structure, some ideas that we followed in order to keep the code in particular small, even though some of the features have quite expanded in the past. So a lot of the motivation I don't have to give anymore because it's happened plenty of times. So my point here is that computational material science is here to stay, and we see this in particular from one of my favorite plots, namely the computational usage on the Archer 2 supercomputer in the UK. I picked that because the data is easily available on GitHub. And the dark blue here is just density functional theory, so the very model that the density functional toolkit is solving. And you can see very consistently that there's about a third to a half of the computational time that is spent on that particular cluster. I mean, nowadays, with more and more compute being specifically invested into LLMs, I would say the statement that 30% of the world's compute is used for material science is probably no longer true. But certainly on, let's say, academic-grade supercomputers, that statement is still true. And I mean, a good share of this 30% is running DFT. So basically, what's a bit the motivation for the density functional toolkit is to provide a framework for experimentation, in particular for people from math, people from computational science, and to be able to really interact across multiple disciplines. And so for this reason, we've made it feasible to restrict yourself to simple model problems, but also do cutting-edge calculations. And I wanted to say that, you know, we are still on the order of 11,000 lines of code. So to give you some perspective, state-of-the-art codes are more in the order of hundreds of thousands of lines. So VASP, as has been mentioned in an earlier talk, I think sits at 300,000 lines. So basically, we are an order of magnitude smaller. Still, we have really a bunch of standard and not so standard features. So in particular, I want to highlight here hybrid DFT calculations that are still experimental and that we recently got working, which in the solid state code is in fact not such a simple endeavor, which was, by the way, an external contribution. So this is not something that our core team did, but somebody externally contributed. So we talked about algorithmic differentiation, or much rather Bruno did that. And I will mention that we have integration with a lot of GPU-related features. And before I go into the main part of the code, namely of the talk, namely showing some code examples, I just wanted to highlight the performance aspect here. So I'm comparing in particular, again, to another standard code in this field, Quantum Espresso. And the absolute numbers are always a bit tricky to interpret, so don't take these too serious. I think the main point when you're looking here at the comparison of the two codes is to say that, you know, they're actually not, I mean, we as DFTK, being Julia-based, are not too far off, right? There's a bunch of examples, like here's an aluminum supercell, so like a catalytic surface, where we are noticeably faster, but then there's also still some systems where QE or other codes are winning. And here this is scaling across multiple GPUs. So here we're basically taking a silicon supercell system and we're scaling it up to 4 GPUs. So it's something that we are really actively investigating, scaling and larger performance. And I should really say that this AD pipeline that Bruno presented is fully ported to the GPU. So in some sense, the GPU abilities and the AD capabilities, they fully compose. Okay, so that's sort of for the hopefully quick introduction. And now I wanted to go a little bit more into how is it actually to work with DFTK and how do we internally use a few tricks to keep the code base small and manageable. So this first tutorial here, Bruno again also discussed. So the idea was here to take some system, load it from an external file, use an atom space. We have some programmatically tabulated pseudopotentials. That's basically a key ingredient for modeling how electrons and nuclei interact, which is needed for plane wave calculations. You can compose a model very easily, basically specifying all physical details. Afterwards, you decide on the discretization. Again, there's some heuristics for standard pseudopotential models that help you choose cutoffs and K-point grids, which sometimes works, sometimes doesn't. So this is a complicated endeavor. We haven't solved all the problems there. And basically a self-consistent field call in more or less one line. And on top of this, some post-processing, for example, plotting a band structure, pretty classic code. And what I wanted to first mention about the customizability, so this code has been highly motivated from mathematical research. So for us, being really able to just modify any of these algorithms in place without changing the core code was crucial. So here, for example, I'm implementing one very simple approach to solving these self-consistent field fixed point problems. So it's a fixed point problem, so the classic way to do this mathematically is a damped iteration. So this part here is kind of the update step of the fixed point function, which DFTK exposes directly as a callable Julia function. So there's a lot going on whenever you call this function. It's diagonalizing a large system, basically a nonlinear eigenvalue problem, a linearist version of this, a large Hamiltonian with an iterative diagonalization procedure. If it's, for example, GPU-based, then all the details of the communication are completely hidden. And you, as, for example, the mathematician coming up with a new algorithm, you can directly take this function and write sort of the core pieces of code that really make up the algorithm. And you can slice this in and start playing, for example, Pluto ways with the parameters, and in particular, as I mentioned, be able to immediately get this to the GPU. Now, the first thing I want to mention in terms of code complexity is how about GPU, how about making GPU feasible? So, of course, there is the great Julia GPU ecosystem that takes the core load away from us, but there's a few details that one has to keep in mind. One of them is, for example, that the core libraries that we use for implementing models, like these thousands of possible DFT models, they are supplied by the electronic structure community and are unfortunately not always easily callable on the GPU. So for example, here we have a little bit of glue code that makes sure that if you have a GPU infrastructure that is not available inside this external third-party library, then automatically the computation takes place on the CPU. And there's a few performance-related small patches we had to apply to overall make sure that the performance is reasonable. So what I want to mention here is that basically in the order of 70, 80 lines of code that are GPU specific, we have a full generic GPU implementation featuring both CUDA and AMD GPUs. Okay, so the inverse materials design example here I'm going to skip because Bruno has explained it. It's basically the same type of code that he mentioned about training a band gap. What I want to, however, go a little bit more into details is how algorithmic differentiation not only helps us from the point of view of a user to make it very powerful and start thinking about these new capabilities like optimizing properties of materials or coming up with better functionals, but also how it helps us internally to keep code small. So many property computations, as Bruno has mentioned, are derivatives, right? And so as a result, this also applies to typical computations that take place in DFT codes themselves, such as stress computations. And here I have a slightly compressed version of the entire stress implementation of DFTK. Right? And since in the end, this is just a derivative of an energy function, this is more or less how we implement it, right? So we have a particular function to evaluate the energy in a way that the so-called Hellman-Feynman theorem can be exploited, And in the end, this is what goes here into a forward diff gradient call to compute this derivative. And in the end, we have a few options to make, for example, forward diff a little bit faster. And we need to, for example, here take care of some symmetries. So my point is that the entire code to really compute this type of problem here is maybe on the order of 30 lines, right? Now, you would say, okay, sure, what's the big deal? Well, the big deal is that classical codes, such as, for example, Quantum Espresso, need a couple of thousand of lines. And in particular, this is hand-coded for every type of DFT problem. So maybe you notice here that there's nothing in this piece of code that depends on the exact DFT functional that is used. All of this is hidden here in the model and in the energy evaluations, which means that if some people come up and really extend DFTK, for example, by making such hybrid DFT methods that I mentioned earlier available, this stress code, more or less, immediately works, right? So this is not just 30 lines of code that we have now, and they keep us from writing these thousands of lines, but they also, in the future, they are somehow future-proof, if you want. The same thing I wanted to mention we do for the exchange correlation kernels. So what is the exchange correlation kernel? Well, this is the second derivative of the DFT exchange correlation functional with respect to all its parameters. Now, the point is that when you're doing these density functional perturbation theory calculations that Bruno has mentioned, this is exactly when you actually need to take two derivatives of the definition of your DFT model. So again, taking two derivatives and computing all of this by hand and implementing the code for thousands of functionals, that really doesn't scale well. And so our idea here, and this is really the credit of Bruno, who had this idea, was to say, well, okay, let's again use algorithmic differentiation to compute the second derivative for us. So this means for us, actually, the implementation of the kernel is more or less this function plus a little bit of glue. Right, so I'm hiding some details, so it's maybe on the order of 50 or 60 lines of code, but nevertheless, the key point is that we have already anyway a function that computes the potential, so basically the first derivative of this energy, because there's a lot of hand-coded optimizations, and so here we're just taking the second derivative as well on top using algorithmic differentiation. Now let me just show you one more example which I really like to close off. And this example is something that combines both algorithmic differentiation and an aspect related to error control. So some density functionals that have been proposed are probabilistic in the sense that they have probabilistic distributions of their parameters. So one is the famous beef functional. So actually, you see it's not just one model, but an ensemble of models. And so what we have been able to achieve exactly using algorithmic differentiation is that we are able to push this ensemble of errors all the way to band structures in the sense that this, for example, gives you error bars on the band structures that come from the probabilistic density functional that is used underneath. And in particular, what I want to highlight is that this works not only for what we call fixed letters, but also for relaxed letters. Because of course, if you change your functional, you actually change the optimal geometry of your structure. And so therefore you have two contributions, one from the geometry and basically one from the uncertainty of the functional in itself. And so this is something that, again, was feasible just composing from the individual building blocks that we have made available, errors and density functionals. Okay, I think this is a good time to stop. If you have questions on what I showed or more on DFTK's implementation details, I'm very happy to take them.
Thank you very much, Michael. Let's have one or two very quick questions.
So if I can propagate my errors all the way to the thing I want, like the band structure, can I in DFTK then reverse engineer my convergence settings based on getting my, like basically converging on the band structure accuracy rather than setting the convergence settings for the SCF?
Yeah, we're not there yet, but that's would be, of course, ideally what would happen, yeah. Yeah, so another project with Bruno, we're working, for example, on discretization errors. So basically, how large should your cutoff be? And there, I mean, for example, it suggests that one is able to reduce the cutoff in certain situations, but still gets an estimate of the accuracy of the result.
Yeah. Thank you. Very interesting. I wanted to ask, so if you have the automatic differentiation, is then also the equation you sort of get out optimized? Or let's say you would implement something by hand, can there be some sort of, can it be improved by sort of evaluating some equations, factorizing something out, or so what do you think?
Yeah, I mean, this is, it depends very much on the framework. I mean, the more modern framework like Reactant, that's sort of their point, that they don't just translate the equations and give you the derivative, but also do optimization passes on top. With forward diff, this doesn't really happen. That's why we're also looking into Reactant right now. as an option. But with forward diff, at least what you can do is usually you know what are the parts where the computation is really spent. Like Bruno mentioned, that it's actually this response problem that really costs most of the effort, and that's why we basically have a couple of works improving the algorithm of these response solvers. And then, of course, the added benefit is that every time you use the AD system, it uses these optimized solvers, right? So we know what are the bottlenecks, and there we spend the effort coming up with good algorithms.
Thank you very much.
All right, thank you all for coming, and this concludes the 2026 edition of the Julia Mawson Mini Symposium. Let's thank all the speakers again. And do not forget, we have the poster session at 7 p.m. and we have a set of Julia Mawson posters there. So I will see you again.